Okay, we're not starting for another 5 minutes. We just want to check whether it works, whether you can hear us and see us. So please, someone write in the chat if you can either or both.
Yeah, here both of us, because we found out that it's a bit fragile.
Excellent.
Oh, great.
Great. Okay, fine. Excellent. Well, then I guess we'll start in 5 minutes. I'll be muting myself until then. Okay, hello. Welcome to the second ACM SIGPlan International Workshop on Functional High Performance and Numerical Computing. So I'm going to do a little bit of introduction to our workshop and talk about what we have on the program today. So first, some background. Maybe you already know this, but Fhpnc is a merger of FHPC, the Functional High Performance Computing Workshop, and NPFL, the Numerical Programming and Functional Languages Workshop. And FHPC ran for a bunch of years, and NPFL ran for just 1 year, and we decided to merge them to try it because they were a good fit for each other and to sort of create some more activity and bring the communities together. Fhpnc was first held in 2019 in Berlin, and then it was supposed to be held again last year, but maybe you noticed the pandemic that occurred, so we decided to cancel it because, from our perspective, the point of these workshops is partially to do some presentations and publish papers and so on, but a more important aspect is also to do some networking and meet people and talk to them, and we were not really seeing how that was possible with an online workshop. So, yes, as you may have noticed, Fhpnc is virtual this year. We didn't cancel it for a second year. And the reason for that is that we fear that if we cancel Fhpnc again, it might be canceled forever, and we didn't really want that. Also, we actually tried attending some of these virtual conferences, and we got some experience with how it works out. And while it's still not as great as a physical conference for the purposes of networking and such, we think that it'll serve at least for this year, and hopefully it'll be physical next year if at all possible. So we've tried to kind of make some changes to the program and to the format to kind of replicate the physical workshop experience in a virtual environment, and I'll talk a little bit more about that. So our program, the main part of our program, is the presentations of research, which is based on 4 papers that are in the proceedings and 1 extended abstract, which is not in the proceedings. Then we have an invited talk by Sven who is perhaps most known for designing and implementing single assignment C at a time far before anyone thought that, or not far before most people thought that functional programming was useful for high performance computing. He'll be giving a talk. And then we have what we call a community update, and this is one of the things we introduced to kind of compensate for the fact that Fhpnc is virtual this year. So this community update are summaries given by representatives from various groups in our community about what they are doing and what they hope to be doing in the future. And this is supposed to be a springboard for further networking and discussion and potential collaboration. So it's not research presentations, it's really about what you want to do in the future, not what you have done recently. And then after that, we will have our usual informal discussion on the future of Fhpnc. For example, if it also has to be virtual next year, should we then only have it every other year, or should we just also have a virtual Fhpnc next year? Hopefully it'll be physical next year, but you never know in this environment. And the usual discussions about how we increase the amount of activity and how we reach out to other communities and get some collaborations going. The informal discussion will be held in the lounge area on Airmeet, which will allow everyone to talk, not just me and Gabby. Yes, so a little bit about the submissions this year. So Fhpnc is a small workshop, but it's a workshop that uses a classic mini-conference rigorous peer review process. So every paper receives at least 3 reviews from our program committee. The extended abstract also receives reviews, but it's mostly just to see whether it's sane at all. It's not a rigorous review process for the abstracts. And of course, we are very grateful to our program committee members for putting in the time to do all these reviews. This year we received 5 paper submissions and 1 abstract, of which we accepted 4 papers and the abstract. So that's not a lot. It's not much less than last year, where we had 6 papers and 4 abstracts. It's mostly just much fewer abstracts, and it's kind of comparable to what FHPC had in the old days, which didn't have very many papers in the old days. We didn't have abstracts at all. Still, it's not as much as we had hoped for. And I don't know whether we should advertise more or whether it's just because of the pandemic, which kind of lowers the incentive to submit to these workshops. But we can talk about that at the discussion at the end. So then we should move on to the presentations, unless Gabby has something she wants to add. Nope, she doesn't. So here,
just welcome everyone and thank everyone that you kind of joined us this Sunday morning.
Yes, thanks for joining. So for the presenters, I'll just mention briefly how it will work, because I don't know how many of you have tried AirMeet before. You will be brought on stage, which means you will be added as a presenter like I am now, so you'll be able to stream your audio and your video. And then you can press a button at the bottom of the screen saying present, I think. And then you can either share a window or you can share a PDF file of your slides. And I think the latter is perhaps simpler for most people. That's what I did with my presentation here, because in my experience, that's more robust than actual screen sharing. If you want to try it out in your own browser, you can always go to the lounge and find a table and present there. I think it uses the same infrastructure. So if it works there, it should also work here. But for now, I'm going to bring on stage the first presenter, who is Federico Pizzuti. Sorry if I butchered your name, who will be talking about generating high-performance code for irregular data structures using dependent types. And let me see here, invite to stage, and then I think he has to, yeah, here he is.
Hello, can I be heard?
Yes, I can hear you.
We're fine? Okay, great. Let me select the PDF file.
And then I will hide myself because I'm not the point anymore.
Okay, let me see how I can control it. Preview slides. You know I can control the PDF. I'm not entirely sure how to change the slides. Let me just screen share. I think it'd be easier. Okay, everything good? Do you see the slides and everything? I guess so. Perfect. All right, well, hi, my name is Federico Pizzuti. Present my work with my two supervisors, Michel Stueyer and Christophe Dubach. And we're going to talk about generating high-performance code for irregular data structures using dependent types. So I'm in the business of data parallel functional languages. These are languages that try to answer the problem of programming parallel heterogeneous hardware, which is quite a difficult task. The idea is that we're going to use the properties of functional languages, so the high-level nature of them, plus the correctness guarantees and the ability to generate efficient code. And we use this sort of system extensively for what we call regular data applications that work over relatively regularly shaped data. However, irregular and sparse data structures are not just as well supported as the first use case. The goal for this talk is to show how can we provide a basis for the first-class expression of such sparse and irregular applications. And we're going to kind of build up from the basics up to the desired level. So how the setting of these languages, again, how they work, we tend to use types to represent the shapes of data structures. We use algorithmic patterns to express data transformations. And then we use kind of algebraic reasoning to express, through rewrite rules, optimizations. And these are the ingredients that hopefully will give us a compiler which can generate optimized parallel code for sort of GPU targets, for example, in our use case, but it could be other targets, your kind of low-level parallel target. In this talk, we will focus on types. The rest is kind of in the background. It's still there. In fact, our goal is to extend our type system to leverage the machinery that is already there. But we will not talk about compiler details per se, more like type levels. So we start with the most basic type, the type of a regular array. And that's the notation we use. I'll explain it very shortly. So n is the length of an array known at the type level. Delta is the element type of this construction. We can nest arrays together because arrays are themselves data types. The reading is kind of right associative. So n.m.delta means n arrays, n sort of outer arrays of m of delta. So 3.5.float32 would be an array of 3 arrays of float32s, each inner array length 5. This kind of array types can be used to describe the semantics of many of the common data parallel patterns. For example, in a map type, we could say we take a function from t to u, and we take an array of n.t and a return array of n.u. So we're not going to change the number of elements because we're mapping. While in a reduction, for example, we're going to shrink the array down to an element. And we can also model other type of primitives, such as split and join, would say reorder the elements in an array. So we can say, give a certain length, I can try to split the array, group things. So these array types are very rich and allow to talk about these problems we care about. And they can be used again for many applications. Linear algebra is one of such examples, but also stencils, such as convolutions, acoustic simulations, image processing, such as filters. All this work over grids, and this works very well. Just give an example for this paper, for this talk. We kind of run through this example. It's the sparse matrix vector multiplication. So given a matrix and a vector, we write a functional program, which looks sort of like this. We have some inputs of which we give types because we need to specify the shapes of our data. And then we use some standard functional notation. We use this reverse function application for like simplicity, but that's nothing new. The compiler of this data parallel functional language then can use all this information to generate quote-unquote efficient low-level code. Now, in this talk, we'll not talk about parallelism. We only talk about other concerns, so I'll just show sequential C. But even in this sequential C, we notice that the loop bounds have been inferred from the types. The loops, the map and reduce loop, have been fused together, so we can do this kind of optimizations. And also the matrix, which is a two-dimensional array within our kind of type system and logically, is actually implemented as a flat buffer. And the array can figure out the flattened indexing thanks to the kind of algebraic properties of what does it mean to index into an n.m.float32. However, we have a limitation. The shape must be regular. The types can only represent rectangular grids, and no amount of nesting these arrays can ever give us anything more. But what about other shapes? For example, triangular matrices. Well, we need to generalize the type a little bit. We say we still have an array, which is like an end dot something, but instead of having a single sort of type, we have a sort of a function. Actually, more like a lambda, right? We're scoping the index. This I ranges from 0 up to n-1. So I kind of takes the value of every of the index for every single element, the next index. And the actual kind of the element type is going to be dependent on I. So we can think of it as a function of I. So this f is a kind of a function from natural number to type. In fact, the whole body of this array is actually a type level function that takes a nat and returns a different data type. For example, again, the triangle example, we could say there is a triangle whose height is 5. So we can have an outer array of size 5. And then the inner size is I+1. So an array of I+1 floats, where I is the index of the array. How do we use it? This is position-dependent arrays. Very much the same. We have to, of course, update the type. So, for example, if we're doing a sparse matrix vector multiplication, we change the type of our matrix to use this new formulation. But we pretty much leave the rest untouched. And now the compiler, again, this data parallel compiler, can generate efficient code, which very much resembles the other one, of course, with some interesting things. For example, now the inner loop is limited to the outer loop because now we have this kind of dependence. And also, the matrix is still a flat buffer, and the compiler can figure out a closed form formula because, in general, indexing into this kind of position-dependent array could be arbitrarily complicated. You might have to run a loop to figure out your index. But the compiler can figure out that actually there is a closed form formula. And this is very similar to polyhedral kind of optimizations, that kind of space. You just figure out what the formula is from the algebra. Okay, but now we want to talk about irregular applications and sparse data. So let's talk about Csr matrices, which can be a very good example. So a Csr matrix is a sparse matrix. So we have a logical idea of a matrix, but in actuality, we store it in a compressed way. So instead of having just the values, which are the non-zero values array at the bottom of the slide, we also have row offsets, which is kind of metadata that give us the structure of the matrix. Each row, the length of each row is the difference between the offsets, the start and end offset. And also we have column indices that help us reconstruct the structure, because for each row, we need to know where in the column a value is. So what if we wanted to express this kind of shape with the types we currently have? Well, it's going to be a matrix. So we have an outer matrix dimension. There's going to be some kind of position-dependent array. We know that much. We know the element type. We can kind of zip the column index and the values together. So we can say you're going to have the float, which is the non-zero value, and some index bounded up to m, which is the kind of column index, because it's never going to go over m, so the column of the matrix. But what can we put there, right? It's kind of how do we express this? So the problem here is that our position-dependent arrays cannot talk about values, sort of cannot refer to other values. They can only play around with the index, but they cannot introduce dynamicity. Now, in order to introduce dynamicity, we need to introduce a new concept. So let's take a step back. So far, we talked about this kind of natural numbers, and we call them nuts. These are type-level natural number expressions. We use them in array sizes, array indices. Everywhere you see a number at the type level, it's a nut. However, we can extend this with the concept of nuts. So a nuts is an index sequence of natural numbers. So it's fundamentally an array at the type level of nut. Given a nuts, you can index it at a given nut to get the nut at that index. So you can also think of it as a function from nut to nut. But it's kind of a reified function. We want to really convey it's kind of an array. And now, if we had such a nuts of offsets, so a nuts called offsets, which contains the matrix offsets, we can now write the type, because we can have the outer matrix dimension like before, and now we can have the inner matrix being this expression. So saying, look at the two offsets, as we said, because the two offsets, like the difference between the two offsets gives you the row length. So this actually, we can talk about it. And now we can actually talk about the values the same as before. So it's a float and the index. So kind of to give a visualization, you can think of it, the offsets is just kind of an array in memory, but somehow referable to at the type level. And the data itself is just the sparse matrix, which contains the value packed together with the column index. So how are we going to get our hands on one of these nuts? Well, we can introduce these two primitives, lift nut and lift nuts. What do they do? A bit clear now. So given a value level expression of type either integer or array of integer, we can freeze it and lift it to the type level for some inner scope. So in some inner scope here, kind of expressed as an argument function, the value of that expression can be kind of bound to the type level variable. And then we can compute something, and then we can return the value, which does not depend on the nut and the nuts, because they're not named. So you can use it, but it cannot kind of appear in the type T. And so this is safe. So we can compute and go away. To make a very simple, silly example of this, we could say, given two arrays of integers, A and B, we could sum up the values of A, so reduce the value of A's, and then kind of the result of that reduction, make it a type level construct called count, use it to take some elements out of B, because take wants to know how many elements it wants, because all arrays have known sizes, and then reduce B again. So if we look at the generate C code, the point is that count is both produced by some user code in the reduction and in the type level kind of expressions for the second loop. So now we have a way to link together dynamic values and types. Okay, so how do we deal with this CSR matrix? Well, let's create a function. Let's assume somehow we created these offsets with this lift business. And now we can take a matrix and a vector, and that's it. We don't really need to use offsets because it's only a type level construct. We just need it to scope it. We just need to scope it to refer to it. And the compiler again can now generate the sparse matrix vector multiplication. And as we can see in the generated code, we're going to refer to the indices in these other data structures. So we're actually going to fish out the indexes dynamically, right? Because these offsets could be computed, and this matrix is basically input data. And also, once again, the index has been kind of flattened. And very interestingly, the compiler realized that doing the kind of the summation over all these different lengths is actually just looking up the last offset. So the compiler basically figures out why we want CSR matrices in the first place, which give us fast kind of random access in the middle of the matrix, which we need for parallelization fundamentally. Very good. We now can produce this kind of structures. But now we kind of have a problem. What we want to write another program. We want to write the program dense to CSR that takes a dense matrix and generates a sparse matrix. What would the type of this program be? Well, let's say we take a dense matrix, which, as we saw before, it's an n.m.float32. That's fine. And then let's write the return type, which we just give for a sparse matrix. And now we have a problem. This offsets is somehow leaking out of the body of dense to CSR, because ideally, offsets is computed from the matrix, right? It's kind of with this lift nuts, we're going to generate it, and then we're going to use it, and now we want to return something, but now we have like an unbound variable out of our function, and we need to call the plumber because we cannot leak variables in the scope. So what are we going to do? Well, first off, we must realize that this is not the program we're looking for. Absolutely not. This is the program we're looking for. We take a dense matrix, and we're going to return both offsets and a sparse matrix. In order to look at the sparse matrix, you need to have the offsets. You cannot make sense out of it. And so it's not really a symmetrical pair here. They're not equally good, these two values. The first one is necessary for the second one. So we cannot express this construction currently in our language. We cannot say these two elements, pack them together, and introduce this dependence. We cannot create enough. We cannot do anything. But as people know dependent typing would know, there is a solution to this problem. It's called dependent pairs, which is what we introduced to the language. So what is a dependent pair? Well, it's a pair. So it's made of two things. There is a named first element, and the name is kind of a type. This is type, right? Where we're talking not the value, we're talking about the type. So the type is named, and the first element can only be, for in our use case, either a nut or a nuts. We don't care about having kind of generic dependent types, because that would be really hard to compile efficiently to a GPU. So for now, we just restrict what we know. Name first element, and then the second element, the type, is dependent on n. And again, we use this formulation where the type is basically a function of n to talk about a type which is dependent on n. For example, so in many languages, arrays have kind of dynamic size, right? You kind of represent them by writing the size as a kind of a header and then the body of the array. And so far, we couldn't do this in our language because our array sizes are kind of only known at compile time because we want to elide it away. But if you wanted to have this level of dynamicity, now you can, because you can say fundamentally I have a dependent pair whose first element is a nut n, and the second element is an array whose length is n. So now we can actually express a sort of dynamic array whose length is kind of encoded within the value itself. How do you construct a dependent pair? Well, given if you give two things, so if you give, say, a nut and something who depends on that nut, we can package them together and sort of record the dependence. This recording is done from the fact that this I turns into n. It's just kind of standard trick. Now it's independent, right? It's kind of encapsulated. And how are we going to access it is a bit more complicated, because, of course, we cannot give first and second projections, because second projection would make no sense. Again, you need the first thing to look at the second. So we're going to give you something called match, where you take the whole pair and you pass in a function who takes the two values separately. And now we can use kind of dependent functions to express the fact that the second argument must depend on the first, right? And then they compute some type t, which again does not refer to I in this case. It cannot refer to I. And once we return, we're done, and there is no more dependence. And if you want to kind of carry around the dependence, t itself would have to be a dependent pair, right? You can match it apart, do some computation, and put it back together. So that's the kind of setup where we use dependent pairs. And now with dependent pairs, we can actually give a proper type to our CSR matrix, because we can say that the CSR matrix of size nm is actually, oops, sorry, my bad, mouse scroll, is actually a dependent pair, where the first element is the array of offsets, which is a nuts, right? And the second element is the kind of the data in a column indices who depend on off, using the formula we saw before. And now this is a self-contained item, right? There is no dependence anymore outside this bundle, which means that we can write dense to CSR. We can take a dense matrix and generate a sparse matrix. This is not only for sparse matrices. You can represent, of course, other data structures. Graphs are commonly represented in a similar way, where you have a kind of array of offsets, which kind of defines slices. And then for each node, you have a slice, and the slice has the index of the nodes this node is connected to. So each edge is kind of implemented with this two-level way. And once again, we can just use the same structure and use a different element type. Instead of having the float and the index, we just have the index. So we only care about the node address. So how are we going to evaluate the kind of, this is still functional high performance computing. This is high performance. So for now, we show the results of evaluating dense CSR and sparse matrix multiplication, the implementations we give in the paper. Our compiler generates OpenCL code, so it targets GPUs. In particular, I've been executing on my NVIDIA 1080 GTX that I have on my desktop computer. The reference implementation is the NVIDIA QSparse sparse linear algebra library. So it's kind of a state-of-the-art linear algebra library that actually uses CUDA and it's kind of native for the GPU. All the graphs I'm going to show you give speed up related to QSparse. So all numbers are kind of on the baseline of QSparse. So the first evaluation is the dense to CSR. So on the x-axis, we have the matrix dimension. And on the y-axis, we have the speed up, because again, we give relative speed up. And these are for different matrix densities. So different matrix densities change the performance characteristic of the program significantly. And we can see that in most cases, we're quite faster than QSparse, 1.5x, 1.2x, some cases even more. We suffer a bit on the dense matrix side, but nothing can be perfect. Still, very competitive with QSparse. And the second one is the SPMV. SPMV, sparse matrix vector multiplication. On the x-axis, we have a set of kind of commonly used matrices, sparse matrices throughout the literature. Many papers use this, so I kind of sampled from them. And once again, we can see we have speed up. We have a mean speed up with QSparse, and in general, we are competitive. So yes, so basically, this approach allows us to be competitive. Now, I want to stress one thing. This is not because of the types. The types didn't make our programs go fast, right? The types only allowed us to leverage the machinery of data parallel functional languages, which has been built kind of over a decade by kind of the community of research. We are just, it's kind of a low-hanging fruit here, right? We're working on the expression size to kind of leverage what the machinery already can do. So the talk I gave here kind of covered several years of work, kind of gave you a vertical slice of the work. Started for me at least when working on Lift, so ICFP 15 paper, where I introduced the system with the regular arrays and that sort of setup. I generalized this to the static position dependence, so the triangle stuff, which was presented actually at Fhpnc in 2019. The idea of using a dynamic value to be able to express sparse matrices comes from CC20. And then in this kind of paper, we extended it by providing dependent pairs, providing the lifting, and in general, doing a makeup of the whole system to make it all kind of work together nicely and formally. And also, we combined it all together to be able to support this kind of sparse application on both sides. So now you can compute, you can consume sparse data structures like sparse matrix vector, and you can produce sparse data structures. So you kind of have the full picture in a sense. Of course, there is much more in the paper. We talk about the type system in great detail. We give there were three case studies, dense to CSR, the sparse matrix vector multiplication, but also the breadth first search over the graph, which didn't make it for the presentation, but it's all in there. We also talk about code generation and optimization, and there is some detailed performance analysis. And actually, that's my presentation, so I'm happy to go and take questions or anything else. Oops, I will.
Yes, and I don't. Where is the applause button? I don't know.
Well, thank you very much.
Yeah, great.
Plenty of emojis. I feel very happy.
Yes, and there's also a bunch of questions. And
okay.
People can still go in and ask questions in the QA tab to the right of the video stream, and you can upvote questions, and I'll post the questions in the upvote order. So I'll start with this one, so do you rely on later phases of the compiler optimizing the add and multiply into FMA, or can this be done at MapReduce fusion time?
Sure, what FMA do you mean?
Fuse, multiply, add.
Okay, no. So the way it's done, it's basically the compilers. So this this is explained better in a paper we could publish about the compiler architecture. But the general idea is that all our primitives are kind of lazy and then there is a kind of a whole system machinery to kind of generate values in a pool-based fashion. So the map basically doesn't do anything; it just kind of wraps around, and then when you go generate the code of the reduction, right? You kind of wrap around, and then ultimately you're going to generate the output value of the program. And as you walk back, okay, what did it take to generate the output? Okay, the last thing, so on and so forth. It kind of starts pulling out values and kind of introducing copies where necessary. Yeah, you specify where to introduce copies. So in general, everything is fused directly. So it's basically a later phase of the compiler, but not really an optimization. Is like the actual structure of the compiler. Like everything works like this in this compiler. There is no way around it. I hope this answers the question. I'm not sure. We can expand later if necessary.
Well, all Michael has answered. So the next question is, does the compiler rely on or take advantage of types during optimization, or are types only used for verification?
Extensively. That's basically the optimization come out of this system. Basically, all the information the compiler has is through types, and any sort of optimization is through types. Now, some of the optimization is really fundamental. Like I showed you when you are accessing a position-dependent array, we are, in a sense, inferring the flat closed form formula. This is technically an optimization, right? But it's kind of a necessary optimization. Without this, this would be unbearably slow. But there are also other optimizations, of course, that take advantage of these types. But a lot of them are in the algebraic space. Like we can prove things are equal and kind of remove operations, or inline loops that we know, of course, they have a fixed size and stuff like that. I mean, the standard gamut of optimization. So yes, very much so.
Okay, nice presentation. I agree. Is there any strong reason to have a net type separate from arrays of indices? We were thinking of implementing something similar, but we're planning to use arrays that are in scope as sources of sizes for other arrays.
Yes, the main reason for this is to kind of keep it manageable, because if you allow an expression to be inside your type, right? If you say, okay, now I can put an expression whose type is array of index inside my type. Well, now I can put map of something inside my type, and I can have map reduce something inside my type. I can have a crazy program, right, that does something insane inside my type. So this is technically okay, right? There is nothing fundamentally preventing you this, but I found this to be very hard on the implementation side. So the idea of saying you first compute it, and then you lift it, and at any moment, types are types, values are values, and the link up point is just this lift nut. So it's more of a strategy for the compiler writer. There are, of course, alternative formulations where you could imagine that you just inline the program within the type, and then you kind of do this kind of pulling it apart kind of mechanically. This was something we presented in another paper. Did this just for clarity? I think it's cleaner to express it in this other way. But yeah, sure, you could do it.
All right. So now here come my questions. So could similarly fast code be written with data parallel functional programming without dependent types by implementing the code with flat arrays with manual offset computations, which is presumably what your compiler does as an intermediate step anyway? I think so, yes. I mean, we live on a space, right? On one hand, there is a C where you like do everything manually. And on the other hand, there is like this stuff where you try to kind of keep up the illusion of, oh, it's actually a matrix, it's two-dimensional, we map over it, we fold over it, and stuff like that. And then, of course, there's something in between where you could say, actually, it's a multi-dimensional array, but it's actually an array. You actually pull out indices, kind of a bit like what single assignment C does, I think, right? It's kind of like you have a multi-dimensional arrays, but then you pull out indices and you do manual indexing. You could do that, of course. And another thing to point out, however, is that we're working in a parallel context, and there is a point where this interfaces with the rest of the language, right? So we want our parallelism to be in our map. So the thing you want to be parallel over needs to be an array dimension, because you need to map over it to know how much to parallelism. So if you do this kind of system where mapping tells you basically everything about the parallelism, then I think, and if you want to map in parallel over a sparse data structure, then I think you might end up in the same place. But sure, nothing stops you from doing something like that, of course. So do you have an idea of how much? Presumably the program that does this manually would be larger and uglier?
Would be larger, yes. Uglier, I mean, beauty is subjective, but possibly. But one thing I can tell you, it will be more error prone. That's for sure.
Okay, then we have a question from Jeremy. Net lifting is a kind of existential quantification.
I think so. So the idea here is, yeah, I think so. Basically, I think you're saying in that scope there exists. Yeah, I think it's a form of existential quantification. I mean, this stuff really interfaces with dependent pairs, right? Which are kind of existential, sort of existentially types. So yes, as far as my understanding goes, this is a form of existential quantification.
All right, and then another question from me.
Mm-hmm.
So does the type checker provide any guidance on when the compiler is able to turn indexing into closed forms?
Well, it will shout at you if it can't. It will tell you, look, I cannot do it. I will generate a for loop for every access you do, which is going to make your program 10,000 times slower on average on a GPU, because now there are no more parallelism. No, but the reality is, unfortunately, I don't think we have a good enough theory for understanding when things are simplifiable and giving good feedback on when they're not simplifiable. I think my supervisor, Misha Steuer, is actually kind of musing on someday having something like this, to actually have a stronger language to talk about how to deal with these arithmetic expressions, with nuts. But right now, no. Right now it's very much like it's put in a simplifier. The simplifier simplifies good. Otherwise, well, you look. The good thing I would say, in my defense, I would say that the programs you want to do, right, with data parallel languages are going to be data parallel. And if they're data parallel, the simplification must exist. It's like it's a fact of reality. If it's parallel, it means you can have a closed form formula. And if you can't have a closed form formula, well, you're trying to do something sequential. I can't do that. But yeah, sure.
Okay, that was the last question in the Q&A panel. Does anyone else have any final questions? It seems not. Then let us give our speaker another virtual applause.
Thank you very much. The best applause I've ever received.
Yes, great talk. So I'm going to kick you off stage.
Yep.
And now it was pointed out to me that we started a bit too early with this first presentation, which is not great because it means we don't follow the scheduled program. So now we're going to take a very small 7-minute break so that we will be on track. We will be following the schedule with the next presentation. So go and get a cup of coffee or stretch your legs very briefly. Only 7 minutes. So I'll see you a 11:45 in my time. It might be something else where you are. Hey Phil, I can hear some background noise.
Okay. I see you and hear you.
I can also hear you. There's some noise. That probably maybe does. It doesn't matter. I cannot see you.
Ah, that's interesting. Right. I welcome. How about
Now
that?
I can see you. Yes, that's better. So we're still 2 minutes away from starting, but maybe you can test your screen sharing.
Sure. Okay. I'll do just that. Now I see my. Do you see the slides?
Nope.
Ah.
I still see you though.
Ah. Okay.
Have you usually present to audience bottom at the below the video?
Okay, I'll look for that.
It's an upwards pointing arrow.
Yeah. Yeah, share screen. Okay. Oh. Window or screen. Okay.
Yes, now we can see your browser. Now we can see your slides. Okay, everything looks to be in order.
Good. Will I just leave that up, Trolls?
Yes, that's good. We'll be starting in 1 minute.
Slightly weird. I can't see what other people can see, but
yeah, don't worry. I also found that confusing, but we can see it.
Yeah, cool. Cool.
Okay, we are back on track with the schedule. So now I would like to introduce Phil Trinder, who will be talking about a new profiler for Haskell on Numa systems. Interesting stuff. So, Phil, the stage is yours.
Thank you very much, and welcome all. Thank you for giving up your Sunday. I guess the good thing is this is the start of ICFP. People aren't yet worn out, so you'll have lots of energy to listen to the talks. And it's going to be a bit tough to follow the last talk, but I'll do my best. So this is work primarily done by Rory McGregor, but also, well, supervised by Hans Wolfgang Leudel and I. Hans Wolfgang's based at Harriet-Watt. Oh, now. Perfect. Okay, so this is about looking at how GHC Haskell works on non-uniform memory access architectures, or Numa architectures. Numa architectures partition the RAM into regions. Each core is associated with a region. It can access any address in the memory, but access to the local region is around twice as fast, and the bandwidth is about twice as great than it is to some remote region. And these are becoming common already. The servers that are running, likes of Facebook and Google, they're running on Numa boxes. And as the number of cores is increasing in general purpose machines, so AMD Ryzen chips in laptops have a Numa architecture. So more and more machines use Numa. So this talk is about profiling Numa. You can understand what a program is doing on a Numa architecture at a number of different levels in the system stack. So you can understand it at the hardware level. There are the modern chips provide counters that record things like how many accesses are to the local region and how many are to a remote region. You can also look at things, so the low-level counters are very detailed and finicky to deal with. There are tools at the operating system level, things like Numactal, and we're going to use a Numa prof tool at that level. Potentially, a language implementation, a virtual machine or runtime system can keep track of where memory accesses are being targeted. And in some languages, like C or C++, you can actually allocate memory into a specific region. But of course, most languages don't use explicit memory management. In fact, no functional language does. But the languages with automatic memory management, like Python, Java, they are the most widely used languages that are running all these clusters and cloud instances. Now, these languages don't have any Numa control of the memory. The opportunity associated with that is the implementations both know what the program is likely to do, it has more information about what the program is going to do, but also it can freely move objects in memory without changing the semantics of the program. So you can hope to optimize the program without changing its semantics. And we don't think there are huge wins here in terms of execution time, maybe only 5% on languages like Java or possibly Scala, but a 5% in the number of JVMs that run globally is a huge amount of carbon and energy. So this study is about Haskell, not about Java or Python, but we think Haskell is a really interesting language. It's kind of an edge case language because it has it places such high demand on the memory system. It has massive allocation, deallocation rates, gigabytes a second. Why is that? Well, state is immutable. If you update a data structure, you replicate at least part of the data structure. So you're forever creating new objects. Likewise, lazy evaluation means that closures are being continually constructed and destructed as the evaluation proceeds. And this drives this massive allocation deallocation rate. So in some sense, understanding how Haskell works on Numa is understanding an edge case, the limit case for for language implementations. Ooh, I've frozen. Okay, so I need to tell you something about memory management in parallel Haskell. The Ghc parallel Haskell. The Ghc runtime system uses generational garbage collection. So this is based on the observation that objects die young, and you allocate into the first generation, and you hope to have garbage collected many of the items in the first generation before you fill it. And when you do so, you copy the more long-lived objects into the second generation. The runtime system maintains a separate area for static objects that are generated by constant expressions, so-called CAFs, constant applicative forms. And the runtime system has something called a Haskell execution context, or HEC, for each core. This is where sparked threads of execution that are created by a par construct, where they execute. And since Ghc 8.2, those sparked threads explicitly allocate into the hex Numa region. So each hex is in a region, and all allocation is done local to that region. However, the main thread, which is where the program execution starts, Haskell has a main function, and that's where the execution starts. The main thread is unpinned. It may run in any Numa region. So what I'm going to do is I'm going to report a fairly systematic study of some Ghc Haskell programs running on a specific Numa machine. The machine is called Togian. It's a typical Numa server. It's got 64 cores and 8 regions. And the access latency from each region to each other region is as follows. So the diagonal access latency, these are relative access latencies. Diagonal means access to your local region is fast. It's given a nominal 10, value of 10. Access to remote regions may either be 60% slower or 120% slower. So increased by to 16 or to 22. And you'll see the relevance of that shortly. Okay, so the benchmarks we've studied are 8 benchmarks from the NoFib suite. There's a table in the paper that reports results for all of those programs, but to make this talk comprehensible, we're going to focus on just 3 benchmarks today. The first is Rsa Encryption Algorithm. It's a compute-intensive program. The other 2 programs are versions of a sum-Euler symbolic computation. This is a memory-intensive program. It maps the Euler's totient function over an interval, a large list. And there are 2 versions. There's a data parallel version that allocates a huge list at the start of the execution and then consumes it. And then a divide and conquer version that repeatedly splits the list, creating sublists throughout the execution. And as you can imagine, these have rather different memory behaviors. So the first stage of our investigation was to use existing tools to profile what these programs were doing on Numa. And the first profiles I'm going to show you are Ghc heap profiles that plot residency against time. So execution time is on the x-axis, and residency measured in bytes is on the y-axis. The resident data is attributed to some function in the program in this grayscale, but that detail doesn't matter here. So what we see for this program is, well, it runs in, I don't know, about 550 seconds. It has, initially, it allocates a huge amount of memory. This is the data parallel version of the program that starts by allocating all these lists. And gradually, as those lists are consumed, residency falls. Now, these residencies aren't huge by modern standards, but compared with the other benchmarks, this has fairly high residency and a total allocation of 1800 megabyte seconds. So that's simply the product of the bytes, the resident bytes, and the number of seconds that they are resident. The sum Euler solves does the same computation, but has a very different heap profile. There's constant allocation of the sublists, which means that the residency is fairly steady throughout the execution of the program. It has lower maximum residency, 0.9 megabytes compared with 5 megabytes, and the total allocation measured in megabytes per second is rather lower. And finally, Rsa has a different profile again. It allocates continuously during its execution, gradually increasing the residency. Broadly speaking, this is fairly low, 1.7 megabytes compared with 5 megabytes for the data parallel sum Euler. and a fairly low total allocation, around 9 megabytes a second, compared with 1800 megabytes a second for the data parallel sum-euler. So these are programs. So this is not a data-intensive program; it's compute-intensive. So we choose these 3 benchmarks because they exhibit different patterns of Numa memory usage. These profiles are bog standard GHC tools. You set a run command line flag to generate them. Okay. So the next thing we did was to use the NumaProf tool, which is available. It's an operating system level tool, and we set out to study the access from threads in one region to memory residing in a different region. And so what that gives you is an n by n matrix. In fact, there's an unpinned row here as well. So some threads are not pinned to any given Numa region. And the things to note here, well, blue means low levels of access, purple means higher levels of access, and red means is the highest level of access. So this is a heat map, and red is the hottest, blue is medium, and purple is medium, and blue is cold. So the features of this heat map are a purple diagonal, meaning that each region, threads in each region, do a significant amount of region local access. That's a good thing. Access to remote regions is mostly low, but there's this hot column where threads are accessing, lots of threads are accessing region 3 from every other region. If we look at the other benchmarks, we see very similar pictures. So we again have the purple diagonal, local access. That's good. We have a hot column. Now this hot column, there's always a hot column. When you run the program, the hot column moves around. So these are the results I'm showing you for one specific execution. If you run it again, the hot column may be, the hot region may be a different region. Some analysis, we think the purple diagonal is probably because of the Ghc 8.2 local allocation policy. It's a little hard to understand the hot column at this point. Perhaps knowing how data is how the runtime system is allocating data within regions will help, and we'll return to that later in the talk. Analyzing the data we have for now, so looking at access latencies, we can look at what percentage of accesses are local, what percentage are at distance 16, and what percentage are at distance 22. For sum-euler, there's the 2 different versions, and for PRSA, there's just the one program. And we see that there is a significant amount of local access. This is around that 30% here for the data parallel programs. That is a lot more than you would expect if you had allocated data entirely randomly across 8 regions. You'd expect to have 12.5% local access. So the Ghc 8.2 adaptation is being effective. It's increasing the amount of local accesses. The increase is greater for data parallel programs because they're doing more allocation, so they can take greater benefit from the allocation optimization. we also propose that, well, we'd like to compare these programs. How much load are these three different programs placing on the memory system? And we propose the following metric for comparing that load on the memory system. It's Numa access rate, so it's the number of accesses per unit time, but weighted by the distance of that the access is made at. So on Togian, there are three different distances, 10, 16, and 22. So we compute the weighted access rate in the obvious way. We multiply the number of accesses by the distance, add them all together and divide by time. And we see that the data parallel sum Euler places higher load on the memory system than the divide and conquer, and this is because it initially creates the lists, and that forces threads to make remote accesses, so it places a load which is about twice as great than divide and conquer, which is creating local lists, and so doing more local accesses. Interestingly, PRSA, although it only runs for half a second, is placing a far higher load on the memory system by this metric. So about 3 times greater than, or 3 or more times greater than even the data parallel sum Euler. So that was the information we could gain with existing tools, existing memory management and profiling tools. But we thought that it would really help us to understand where GHC was allocating, which region GHC was allocating memory into, because where you allocate the memory determines all future accesses currently. So we extended NumaProf. We could have looked at this within GHC or within NumaProf. We decided to do it in NumaProf because it already has a malloc tracker called Molt. So you can look where those mallocs are targeted. And we recorded the allocations made by each thread into each region. The code is available on GitHub. So the profiles are, again, heat maps, and hugely unsurprisingly, there is this diagonal where all of the allocation, or most of the allocation from all the pinned threads is entirely local, and there's no allocation anywhere else. That's exactly what the GHC 8.2 optimization does. However, the unpinned main thread does a huge amount of allocation into one specific region, region 3. And if we look again at the other profiles, we see the same pattern. And specifically, the allocation into region 3 exactly corresponds to the hot region in the access profile. So the allocation profile explains the unpinned thread has done its allocation into region 3, and all of the other threads running in all the other regions need to access the data from the main thread, and hence create this hot region. The second thing we thought to do was to look at Ghc Garbage Collection to understand how that impacts on Numa, we are aware that various language implementations, in particular various JVMs, have used garbage collection as an opportunity to optimize Numa. So they detect opportunities to move objects during garbage collection closer to the threads that are using them, i.e. into the region where the threads using them are executing. So that's a big driver for understanding what the garbage collection is doing. So the first thing we did was to record how many garbage collections happen in each region, and of course how many of each type, generation 1 or generation 2 collection, are occurring. These counts supplement a whole bunch of Ghc garbage collection statistics that are already collected. So the number of bytes moved, GC runtimes, there's a whole bunch of stuff collected by the runtime system. So here's what the results look like. So for the 3 benchmarks, how many generation 1, generation 2 collections there are. And I've highlighted in yellow the hot region in each case. To be honest, these results don't tell us a huge amount about Ghc usage of Numa. We see that there's, for example, a lot more generation 2 collections for some Euler. That's because sublists have been allocated early. They survive in generation 2 and force more collections than, for example, in the divide and conquer version of the program. There's a lot fewer garbage collections for the compute and not memory intensive PRSA program, but we don't really learn all that much about Numa from these statistics. The next thing we did was to look at the locality of the objects touched by the garbage collection threads. So how local or remote are they? There's 3 different kinds of objects being, 3 different things being profiled. There's generation 1 collections, there's generation 2 collections, and static objects. And this is similar logically to thread access locality. And in fact, we use the Numa Prof user interface to generate the same kind of heap maps, but these are heap maps of GC threads. What we see for generation 1 and generation 2 collections is good locality. So many of the objects being processed by the GC threads are local, and then small amounts of remote access. Generation 2 is similar, although there is a bit more remote access. But for the static objects, there's no locality. So these objects are evaluated by the first thread that touches them. The threads could be from any region, and so they reside in any region, and garbage collecting them then means traversing potentially many different regions. And we think this could be an opportunity to improve the garbage collection by moving these statically allocated objects to be closer to the threads that use them. Okay, so I'll briefly summarize what I've said. We've profiled Ghc Numa using both Ghc and Numa Prof, so using existing tools, looking at memory residency allocation. We show that there is good access locality, slightly better for data-intensive programs than for compute-intensive programs, but we saw a mysterious hot region, and we proposed an access rate that allows us to compare the loads that different programs are placing on the memory system. We extended NumaProf using the MALT tool to look at allocation locality. Unsurprisingly, there's 100% allocation locality for sparked threads, but the main thread allocates a significant amount of memory into a single randomly selected region, and that region explains the hot region in the access profiles. We extended GHC to look at GC counts per region and per generation per region. Honestly, didn't learn very much. Thread locality, looking at GC thread locality shows good locality for generations 1 and 2, no locality for static objects, and possibly the opportunity to improve locality during GC. As I say, that's the kind of trick that other language implementations have used effectively. So what we've done is we've used the programs to understand some well-known Haskell benchmarks, but we haven't actually used them to optimize them to improve the performance, and that is definitely something that we should aim to do, use the information to improve the performance of some programs. There are various ways we could improve the profiling. The profilers are already pretty slow, of the order of 2 orders of magnitude, and the Numa profiling adds to that, makes that even worse. So the profilers would be more usable if we optimize them somewhat. But the long-term goal is to use what we've learned about how GHC is managing Numa memory to do that better, and I'm quite ambitious. I think for Haskell it might be possible to get improvements of the order of 25% on a reasonably large Numa architecture. And that's it. Thank you for your attention.
Profiling is a bit of a black art, so I'm always happy to see work that tries to explain and develop new techniques. So we are technically at the end of the session, but since we have a break after this talk, I think we have time for questions anyway. So
I thought the schedule meant I could talk until 2 o'clock, trolls.
Sure. The question is whether people will stay around to listen to you. But I'll go through the questions in upvote order. So here is the first one. So the maximum residencies and the benchmarks likely fit in the level 3 cache of the cores and the processors in question. What effect does this have on memory access latency analysis?
Yeah, you're right. These benchmarks are old and small, so quite possibly we should have used benchmarks with that used more memory. We didn't.
So quick follow-up, does that mean we need better or newer parallel Haskell benchmarks?
I think it probably does. There are quite a lot of parallel Haskell benchmarks and lots of versions. I think it'd be fairly easy to increase the scale of those. Good question.
All right, we have another good question, because they're all good. Could the type system be leveraged to determine that a type/array is used only by the thread that allocates it, and to give hints to GC to keep the type Numa local?
Wow. Well, there are, of course, functional languages, non-strict functional languages like Clean that have uniqueness types and are able to do exactly that kind of thing. So in a language like Clean that had uniqueness types, that kind of thing could be done. Haskell doesn't have uniqueness types. I would maybe defer that to people who know more about how to use the type system. So in theory, yes. In practice, I'm not sure.
Okay, then I have two small questions. So how does a profile count memory accesses that hit the local cache?
I don't know. I don't know the answer to that. Hans Wolfgang is in the session, but so he might be able to answer that afterwards.
Okay. Yeah, and I guess that's Numa Prof that will have to be consulted to figure out what it's doing, right?
That's right. That's right. Yes.
Okay, so the last question is also from me. So does Haskell need its own metric for comparing Numa loads? And I don't know how people normally compare these things, but is your metric Haskell specific, or could it be used for any kind of Numa program?
I don't think it's Haskell specific. In fact, a lot of the metrics that are used for measuring Haskell are in terms of bytes. And that's rather strange because the runtime system is allocating objects, and objects are often a lot larger than bytes. So in some ways, we are measuring things at really quite a primitive level rather than thinking in terms of closures or other objects. The metrics I've reported, and in particular, the Numa access rate is measured in, I think it's bytes distance divided by time, but it's bytes. That's quite a long way of saying actually that the metric is low level and could, I think, be applied to other languages. I'm not sure whether people have tried to compare Numa loads before. If they have, I don't know if that works.
All right, let's see. We got one very last late question. Is the current Haskell allocator aware of Numa architecture when it allocates memory? Will this make a difference to allocating in the young generation?
Well, yes. So currently, the optimization, I should have said, is due to Simon Marlowe. He did it when he was at Facebook, and he optimized Ghc 8.2 for Numa because that gave performance benefits for the code he was running at Facebook. And the allocator allocates for Spark threads, all the allocation is done into the local region. So yes, it's Ghc Haskell allocation is Numa aware. It's done locally.
Great. Okay. Well, no more questions. Thanks for your presentation. I will now remove you from the stage.
Okay.
Yeah, final applause.
Your attention, guys.
Yeah. So now we have a rather long break. It's actually the lunch break, according to ICFP. We'll be starting up again in about 2.5 hours, what is at 15 o'clock my time. It might be different for you. Check the program on the Fhpnc website, and we'll be starting with the invited talk by Sven Bodo Scholz. So do show up for that. I think it'll be quite interesting. See you then.
Okay, getting there.
Okay. Do you want to try sharing?
Is a good idea. Reactions, audio, video settings, no. So where is this button? This
On the bottom, there should be there's the camera, microphone, and there should be a sharing icon, a little box with the arrow.
You select share browser, window, or tab. Your entire screen. Okay, let's see what it allows me to do. Okay, macOS says, "Oh, you can't do this. You have to talk to the security manager." Yes, I allow Chrome to do this. Oh no, I have to quit Chrome
Okay.
and come back. Okay, see you in a minute. Oops. Okay, I'm back.
Welcome back.
Well, let's see whether my Mac is happy. Happier.
Yeah, perfect.
Very good. I find this always funny that I have to completely restart the application in order to get this going. Oops, okay. Oh, then it gets smaller for you guys as well?
Yes. Do you want to try it back and forth, like going back and forth? Because I think that was a problem with one of the speakers earlier.
Okay.
Okay, that works as well.
Yeah, it is too.
Okay. Then I
Yes.
think we're ready to get started. So welcome back, everyone. I hope you've got some coffee or any other thing to get you over the post-lunch fatigue. It's my pleasure to introduce Professor Sven Bodo Scholz. And Sven Bodo has been professor at Heriot-Watt for more than 10 years before now moving back to continental Europe, more precisely Nijmegen Radboud University. Fairly recently. And as Charles said in the introduction this morning, I think a lot of you will know Sven Bodo from his work on single assignment C, but he's also done a lot of work on type systems more generally, memory management, generic programming, and partial evaluation. And today he's going to hopefully answer the question whether functional high-performance computing is the key to low carbon computing.
Yeah, thank you very much for having me and inviting me to give this talk. And when the two of you approached me and said, oh yeah, why don't you talk a little bit about your experiences in SAC? I was wondering, should I just, talk about the stuff that we've been doing and where this is all heading, or, and then I started thinking, okay, it has been quite a while that I've been working actually on this. And why don't we have solutions yet? Or do we have solutions yet? Or do we need to invigorate our motivation? And I had a very nice chat with a colleague and good friend from Glasgow University, Wim van der Bavede, just about 2 weeks ago. And we were talking about low carbon computing. And I think this is a wonderful motivation, and I just have to share this with you. So if I say low carbon computing here in this context, what is it I mean? Do I mean FPGAs? I mean, everybody is thinking of FPGAs when talking about, low energy and things like that. No, actually I don't, or at least not exclusively. What I really mean is low carbon in the sense of energy consumption, right? And in particular, I think we should sit back for a second and have a look at how our computing industry affects carbon emissions through the use of energy. And one of the things that we all know is, if you have a supercomputing center, like indicated by the picture at the bottom, these beasts are performance hungry. And if you speak to the people from, I call them the black belt hardcore HPC people, they when they talk about their exaflop systems, and they are wondering how many energy power stations they need next to the compute center in order to make this happen. But that's not all. We also use a significant amount of energy to produce the gadgets that we have. And this is not just supercomputers. No, actually, supercomputers are very small in that. But it is laptops, it's the machines that we have in daily use, and it's IoT as well. It's mobile devices. They all want to be programmed, and they all want to be produced, right? And so why is that such a problem? We are going to use energy anyways, right? We are shifting our cars to energy. So why would computing actually really matter? Okay, let's have a little bit more of a look into this. So I know this may seem a bit off topic, but please do stay with me. So here we have what is called the emissions gap, and I stole this from a UN report, from the emissions gap report of the UN from 2020. And what you see here is, can you see this cursor? Oh yes, you can see the cursor. That's fantastic. You see, we have like about 55 gigatons in 2015 that we emitted, and actually it has become more and more until 2020, although we try to go renewable. And in order to meet our climate targets, we really have to significantly reduce this in the next 10 years. In the next 10 years. Okay. Now, but this is CO2, right? And not all energy is CO2, and we are good at renewables, right? Okay, let's look how good we are really at renewables right now. Okay, here's a report. I was looking for some nice graphics, and this is the best I could find. So this is a report from the European Union, and so it's just European, sorry. But I think it is, well, if it is representative, we are lucky, but maybe it is not. Okay, let's have a look. Let's have a look. The rightmost bar is really the interesting one because that is the mean of the EU. And what the green bar shows is the percentage of renewable energy that we aspire to have 2030. So we aspire to have roughly a third of the energy coming from renewables. May I remind you, we need to decrease the performance here, the CO2 emissions. That means we need to decrease the overall renewables as well, because currently we are already, if you look at the blue dot, at almost 20%. In 2015, we were almost 20%. Now we are at the red bar here. Okay. So what does that mean if we look at the energy consumption, the percentage that computing makes in it, and then extrapolate this on the fraction of CO2 emissions from computing? And if I say computing here, I mean not just running the computers, but also producing new machines with the pace that we currently pursue, and the projected pace from 2020 to 2040. And if you look into this, this is really shocking, because what you see in 2040, we have almost 40% of the CO2 emissions just being a consequence of using the projected amount of energy that we currently do and will do in 2040 for computers and computing. So I doubt this is feasible, to put it mildly. I think this is a very British understatement. The German statement would be, oh my God, we're doomed, right? So this is the kind of thing that we have to bear in mind, right? We can't continue using the energy as frivolously as we do. Okay, what has this to do with high performance computing? Is this Bodo Scholz guy completely mad, or what is happening? Well, I think what you have to think about is we can no longer afford to utilize the hardware as short as we do. People replace laptops and desktops every, I don't know, 3, 4, 5 years. We are not able to continue doing that. We can no longer just expect, in 3 years' time to buy a new generation of GPUs that have TPUs and MPUs and PLLs and DSPs attached to them with non-volatile memory, everything new, and, this will solve all our performance problems. No, we won't be able to do this simply by looking at the CO2 emissions that this would cause. Damn. Also, if you look at, in particular, if you look at supercomputers and high-performance computing, and you see I slowly get to the real core here, then you will see that we actually are not very good at utilizing our machines. And in particular, in high-performance computing, very often we only utilize 10%, 15% of the real performance. Why is that? Well, we burn a lot of cycles in very bad code. So we have to do something about it, right? And at that point in time, I think, we all can make the bridge here in this community and say, hey, hang on. I think this is an old story, right? Isn't that the story that we have always been selling? Right? We have been, since, well, I dare say 20, 25 years, at least, if not 30 years, we have said, okay, we have to use this functional approach. And it is great because it is so beautiful, right? We have high-level abstractions that we start. That's very good because, you can be very effective in writing programs, which is also a very nice buzzword. You can go to industry and say, your programmers will have high productivity. That's a good thing, right? And then we say, haha, once you have these high-level abstractions, then you can think of fold, map, and scan, and you name them. And if you look at most of the projects, at least that are presenting in the context of this workshop, they all kind of do this. They have different ways and different choices. But at the end of the day, it's the same idea. And then you have high-level transformations. And again, we trumpet the FP horn and say, haha, this is just possible because we have such a clear semantics, we are side effect free, and we can prove these algebraic properties, and this is a fantastic thing, the world is good, right? And well, yeah, there is a problem of finding out in which order we need to do these and which transformation we really should apply. But we use sophisticated cost models, type-driven. We use machine learning to do this, and then we have very sophisticated code generators. And this is fantastic. It is like the golden egg, because not only are the programmers predictive, but code becomes very portable, right? Because we can shift the code, we can manipulate the code, and we get high performance because we can adjust it to the target hardware. Ha-ha! So this is the perfect solution. And then what we do all the time is we demonstrate this, and we have seen this in the morning, for example, in the for example, in the lift talk, we said, okay, look, we can compete with Sparse, and that is great. This is a great sign. So if you look at this, and having this smart art on the right hand side of my slide is very intentional, because that's a typical view of the consultant's helicopter perspectives. Oh yes, you should do this, and then all problems are solved. Life is good, isn't it? Okay, I have been singing this song at least, and most of you maybe 1 or 2 years, fewer, or maybe the same time, for quite a while. 20, 25 years at least, if not longer, and others have been singing this song even longer than me. So why don't we have HPC world domination? So why aren't we there yet? That should be all trivial, right? Oh yeah, let's go back. So a few combinators, nice transformation, smart code generation, et voila, problem solved. Why isn't it there? Why don't we have it? Come on, it can't be that hard. 20, 30 years in the making. If you think Sisal, I think, was in the 80s already. They demonstrated that it's possible, but then they didn't get the funding. HPC and high performance Fortran had the same idea in essence. Well, they just didn't call it functional programming, but it was a very similar idea. They promised this within 5 years, and then it disappeared. So what's the problem? And are we crazy? Are we just sitting on our horse and waiting for the horse to reach out for the carrot, which it will never get to? Should we go home and have a swim at the beach, or drink a nice drink, and forget about all this? What is it? Or is it really the Holy Grail? So I don't know, and I will definitely not give you an unbiased answer. I will try to give you an answer from the perspective of the experiences that mainly my personal experiences, but with the help of many students and collaborators in the context of single assignment COSAC. Yeah. And all the technical details you can find on our homepage, more or less. Those that you can't find, please feel free to contact me at any time and ask questions or discuss things. My key how should I say, slogan is, it's all in the choices, right? The difficulties that you face depend on any choice that you make on the road. And there are more choices than one may have bargained for. And the most obvious choices are the language choices. So what are really your abstractions that you have? Is it a map? Is it a fold? Is it an IMAP? Is it a God knows what, right? What exactly is it? How many of those do you have? What are your assumptions about how you represent data? What is your type system? How do you deal with modules? What other language constructs do you support? Okay, then you have to decide how you transform. And there, you know, woo, you have a plethora of choices as well. You know, do you flatten? Don't you flatten? Nest? Don't you nest? Do you bring it all in one particular form? Is that a good intermediate form? Is that not a good intermediate form? And unfortunately, to make things a little bit more spicy, any choice you make at any of these levels influences the potential choices that you have to make at other levels. Yeah. Why should it be easy? Yeah, you have choices in how do you generate the code. Do you optimize for data reuse? Do you optimize for temporal locality? Do you optimize for overall memory demand? Do you optimize for, I don't know what, for vectorization? Or don't you optimize for vectorization? Okay. And when you start thinking about different targets, oh boy, you're in for a surprise. Because not a single choice fits all bills, right? Yeah, if you know, some projects, essentially, I think all projects kind of focus on one primary architecture that they are interested in. And then they try to support the other architectures to some level. The problem is that the target choices are also rather wide, let alone the choice if you have heterogeneous systems with CPUs, GPUs, and you know, different networks and supercomputers involved. And okay, so let's have a look at the choices that we've made in SAC and what, in my view, the consequences of these choices are. And obviously, I can't talk about all the choices, but I try to give a broad idea of the choices, of the key choices that we have made. Right. So overall, that's the basic setup that we have chosen. So when we started out in the 90s, in the last millennium, essentially we tried to get rid of anything that potentially would harm our performance. So we said, okay, no higher order functions. Yes, we love higher order functions, but no higher order functions. And in a way, I think this choice doesn't do our harm. It is a nuisance, yes, because, you know, if you start writing abstract programs, you would like to have higher order functions. But it's not a conceptual problem, because at the end of the day, what you can do is you can do defunctionalization. And, you know, for example, the FUTAC project very nicely demonstrates how this can be done and how this is done. And there's a scheme-based project called Stalingrad in the US who demonstrated that 20 years ago. So it can be done. It is a matter of programming, essentially. Surely it has an impact if I try to sell my system to users, to end users, because they may say, okay, you say it's a functional language. Why don't you have higher order functions? That's impossible. Yeah, and I hear that. Yes, I hear it. But I don't think it's a conceptual problem. Okay, forget about that. Polymorphism. If you don't have any polymorphism, not nice, very annoying. But again, I think it's a similar problem as with higher order functions. We would, if we were to support polymorphism, we would restrict it to a case where we demand that it can be specialized out. So we can make them all monomorphic. And then, so in essence, in a way, SAC is a core language. You can see it as a core language of a language that would support this kind of, I would call it pseudo-polymorphism. Then we decided to have full recursion. And not all the other approaches do that. Some say, okay, you only have tail-end recursion in the form of loops. But I think at the end of the day, the real difficulty in analysis remains whether you have full recursion or tail-end recursion. And as long as you encourage the programmer to use tail-end recursion, I think you'll be good. So I don't think that is a bad decision either. So far, I kind of, how to say, contradict myself in a way. I say these choices are not, in my opinion, not really relevant. Yeah? And please feel free to interrupt me and disagree with me at any point in time, if you have a good argument, that is. The first choice that is really important in SAC, important in the sense that it has consequences and not just minuscule ones, is the choice that we say we want to support n-dimensional arrays. Okay. Most people's reaction is n-dimensional arrays is just n-fold nesting of one-dimensional arrays, isn't it? Yeah, in principle that is true, but we have this idea that we would like to write programs that can take arguments that are arbitrarily deeply nested, and we don't want the programmer to require the programmers to specify recursion to do that. And if you want to do that, then you have to support a notion of an n-dimensional array where you don't know the number of dimensions statically, potentially, at least. Okay. And then we say, okay, we don't want actually crazily nested stuff. We just want to have homogeneous nesting. Okay. This was mainly motivated by the idea to make our life easy. Ha, little did we know. So we said, okay, homogeneous nesting only. That means if you have you can have an element vector where each element is an m by k array, and that means overall it's an n by m by k three-dimensional thing, and these are indistinguishable. You can switch between the view of the two. Okay. Now, if you want to have this, then immediately you have to pay for it. The first thing that you have to pay is actually a payback, and that is the shape of your thingies are now conveniently expressible by simply an n-element vector. So again, if you compare this to the lift talk in the morning, you know, we at this stage we are very constrained, and it's very simple to encode our shape now because it is just a vector of n integers, and that's it. There are no interdependencies between the shape components in deeper dimensions. Another price is that you can't any longer index by just scalars. So even if you have a vector and you say you want to select the third element, you have to provide a one-element vector to select the third element. Why is that? Well, if you want to have shape polymorphic programming, you don't know how many indices you need. So therefore, it needs to be a vector. Full stop, end of story. You can make this a different type, and that is yet another decision. And if you want to go the dependent type route, then this is something that you may want to do. But the basic thing is it has to be a vector. You can call it an n tuple if you want to, but essentially that's interchangeable. Now the good news is programs can be super generic. You can define APL operators in that language directly. Woo, sexy. The bad news is programs can be very generic. Generating good code for generic programs is a challenge because, you know, we have just widened the semantic gap. Okay. Okay, what are the choices then? Well, the first choice, the consequences then. Well, the first consequence is you really need to have an elaborate type system. Because you need to be able to express this. You need to be able to express the shape somehow in the type. And so in SAC, we have made the choice that we want to use subtyping and intersection types because we didn't want to run into the difficulties that we may have to reject programs because the type checker can't prove that they are correct. And so that was our initial thinking, and it is also very convenient for programmers, in particular for end users. So we have over the years had various collaborations with industry, and they found this typing system very, in a way, refreshing, because it was very simple for them to understand. Right, so the end users could deal very well with it, and they were very afraid that it could be something really, really sophisticated. So that's good news. But the bad news is the formal side of this is a bit of a beast. And why is it a bit of a beast? Well, just look at the hierarchy of our types. So on the top level, we have what we call the AUD types. That means arrays of unknown dimensionality. It's just an integer array. We don't know anything. It could be a scalar thing. It could be a vector, matrix, a n-dimensional tensor. We don't know. Then on the next lower level, we know just the dimensionality, arrays of known dimensional, AKD. Here it's a scalar, it's a vector, it's a matrix, and so forth. There are infinitely many of these, potentially at least. And that has implications. Well, because subtyping with infinite hierarchies or with infinite lattices of types becomes interesting if you want to compile modules in isolation and things like that. But I won't dive into the details here. And then we have our most beloved types, the arrays of known shape, which are on the bottom layer here. And there we say, we know the exact shapes. And that's a beautiful thing, because that gives us a lot of information about generating good code. And so if you want to have real high performance, you want to have as much AKS in your program as you can. Okay, generic specification on the one side, that means you typically define in terms of this. High performance code on the other side means you really want to have this. There's just one way to get from there to there, and that is specialization. Okay, this is essentially what I would call the beauty and beast of generality. So let me throw some set code at you. Don't bother to understand all the details. In essence, what this is a generic addition of two integer arrays with the same shape, A and B. And this thing here is called the with loop. That is our n-dimensional construct for defining a new array of the same shape as of A. And we select individual elements in A and B at the corresponding position, add them up, and construct the result of it. So this is a super generic definition, and all of a sudden we have a function add that can be applied to any array you like. And if your dimensionality is 105, there you go, you can have it. It will work, provided the compiler generates correct code and that you have enough resources on your system. Right, and you can easily specialize that. So if you then have an application to two-dimensional things, then the compiler comes along and says, yeah, okay, we have a subtype here. This is the int22. It's an AKD subtype of int star. That's fine. And we can generate this instance, and we can here immediately see that it's a two-dimensional, and you can envision how it's easier to generate code for this. Okay, but I said, in general, what we would like to have is AKS. And yes, oh boy, you can do that too. If I see an application of the thing into a 3x5 matrix, then I can generate this variant. And this goes very well with the overall idea of intersection types in SAC, because this is just an ad hoc overloading. Whether you write it by hand or the compiler introduces it, doesn't really make a difference. Very nice. Okay, you have to be a bit careful. If you have too many of these, then maybe you have a code explosion problem. But in practice, this is almost irrelevant. Good solution, right? Okay, where there's a beauty, there's a beast. Here's the beast. This is a take function, as anybody can imagine. It's an n-dimensional take. So we have an n-dimensional array here, and the shape has n components, hopefully, an n-element vector. And what this does generically, it essentially creates an array whose result shape is the argument SHP, and the elements are just copied over from A. That's good. That's easy, right? So let's specialize. Why not specialize? Okay, here we specialize. We apply this to a two-dimensional matrix here, and boom, boom, two-dimensional, result two-dimensional. Good. Why are we looking at this? Isn't that just the same as the previous slides? Okay, here we apply this to a two-element vector and a two-dimensional array A, and the result shape is it's an AKD type. So why is that? Well, it's simple, right? Everybody knows it. It depends on the values of shape. So we can't. I mean, we could specialize if we were to specialize for values, but hey, that would be okay. So here's a problem, and the problem only comes to light on second look, right? Because on first look, it all looked beautiful when we are looking at add, and there's thousands of operations where the shape of the result only depends on the shape of the arguments. Here it doesn't, and there are just 2, 3, 4 APL primitives that have this property, but boy, they can kill your program. If you start writing programs like that, it is a pain. Okay, so I have this Pandora's box analogy here, and you see the further down we have to go with respect to specialization, and here I added a layer of value types as well, because you can do this straightforwardly. Then your non-termination or code explosion level goes crazy, right? So let me speed up a little. So we have to kind of control specialization. And the good news is, if you dig a little deeper, you can develop a analysis which tells you how far you have to specialize in order to do things. Right? We called it the specialization oracle, but it was a pain. And here you see already, a choice made very early, namely to say we want to have this genericity, and on the other hand we want to specialize, requires us to do something. And it is painful. I can tell you it was painful. It was painful to develop it. It was painful to implement it. And it is painful to debug it when it goes wrong. No? Now, with this specialization oracle, our take problem is salvaged again. So here's our take. And then here's our oracle. What the oracle tells us is, it says, okay, if you want to have a result shape and you don't care what the shape is, well, then you don't have to care about the arguments. It's always true. But if you want to know the dimensionality of the result, well, then you need to know the dimensionality of both of the arguments. That's good enough. And that's the take case on the bottom that I was showing you. But if you want to know the shape of the result, then unfortunately, it's not good enough to know the shape of the first argument, but you need to know the value of the first argument, but not the value of the second. Right? So this is essentially always the most interesting part of this oracle. What is it I need from the arguments in order to know about the result? And with this, I can steer the specialization, and I can actually say, okay, if you know the values here and we don't have too many specializations already, we can do it. We can get this done. So what's the conclusion about the choices made here? Well, it would be nice if you could annotate more. So we would like to have something a bit more towards dependent types, at least I would. But then the problem is, as soon as you want to go fully dependent, just imagine the kind of type signatures that we were seeing in the first talk this morning. I'm not so sure whether the typical users that we had exposed the system to from our industrial partners would appreciate that. Because the average domain expert still has to be able to specify the program. So I think actually what would be nice would be a bit more of a hybrid solution, where there is some help by the compiler, be it some form of inference. So I think this topic is far from being over. Another question is still the question, how far should you specialize? What is really the impact of the code performance? Because there are some codes where AKS specialization is not really required. Yeah, okay. So some guidance there would be a nice thing to have. Another problem is that our nice genericity, I should say outcry for genericity, actually has led to the introduction of index vectors. Vectors means dynamic allocations, right? Unless we have special provisions in the compiler for it. Because a vector is just a normal array. A normal array is dynamically allocated and dealt with in a functional manner. So, okay. A small thing, it seems, but no, it isn't, because now we need to have a dedicated optimization that gets rid of this. Yeah? Well, we can eliminate index vectors. So in fact, we have developed an optimization called index vector elimination. And what it essentially does, it says, okay. In this case, we can totally flatten the generators under the hood. And then we are just dealing with an offset. And this is just a scalar offset. And that can be statically done. But again, it is just, we are asking the question, why aren't we there yet, right? And here's one of the explanations. Because we need to do lots of things that are not totally obvious. The second choice that we have made, and you see it's just getting worse in a way. The second choice we have made is we express all data parallelism by one language construct called the with loop. The idea is you have a rectangular index space, which can be a grid, and then you have several grids from which you know that the union is exactly the entire index space of the array. And then we have different versions. What we do with the values, once we have computed them, we can either generate an array or modify an array or fold an array, things like that. That is very nice because it keeps together the n-dimensional loop nests, and that means we have some better understanding over the entire task and the distribution of the work. In particular, when trying to identify parallelism later on, that is very nice. What is very nice, optimizations and transformations can essentially just deal with one language construct. We don't have 20 transformations, and if you want to do something different, we have to add another 10. No, we only have one. Sounds beautiful, right, at that stage. The drawback or the price is the with loops can become very complex, right? We can have with loops that have 10, 12 different subsets of the indices where they do different things on. They can be arbitrarily nested. Dealing with these rather elaborate constructs is at times difficult, in particular if you want to be able to prove the correctness of your transformations. So I will very briefly and quickly, those of you that have heard about SAC most likely have heard about most of these optimizations, talk about the optimizations that we have developed to deal with this. So we have three key transformations. First is what we call with loop folding. This is similar to what the Haskell world very often calls fusion. In essence, it's the idea to elide intermediate arrays. So here is I always think of these as being large arrays, right? So if you have D equals A plus B divided by 2, then if we inline plus and the division, then, and here I use a different notation rather than the with loop, which is a more recent addition to the language. It's just a short form of the with loop. Oops, a short form of the with loop. You can read it as a set comprehension or an array comprehension. For all index vectors IV, the result is A of IV plus B of IV. So this is how we create an intermediate array. Let's name it C here. And then, we compute the multiplication, which here is 2 times C of IV. What with loop folding in essence does, it just brings these together. It does a forward substitution of the definition of C into this, right? Now, this is totally trivial on this example, but it gets very, very funny if you have arbitrary index sets that you're dealing with here and we're dealing with there. Then you have to intersect index sets. It also becomes interesting if you do C of IV plus something or minus something, because then you have to project where these accesses go to. You know, technical details can be found in a paper, but in essence, this can be done, and this is, I think, the most crucial transformation that we have. Then we have with loop scalarization. So at times you end up with funny codes, and one funny code that you could have is for example a code like this. You could end up with having an addition of rows here of a two-dimensional thing, which are then being added up by themselves. So we end up with an element-wise addition in reality. And obviously, in order to get folding apply as often as possible, one of the things we do is we always try to suck these into a single with loop. So we figure out that actually these are equivalent. The last one is with loop fusion, and that again has something to do with this idea. Any n-dimensional iteration and data parallel operation is expressed by with loop. If we have several with loops that iterate over the same iteration space, it makes perfect sense to join these, because you have improvements on temporal locality and things like that. So in essence, what this means is, once you do these, then you can fuse them into a with loop that has returns two arrays from two argument arrays. And that means just they share the iteration space. Again, this looks totally trivial. It is not once your generator sets become way more complicated. If you're interested in details, again, this lives somewhere else. Now, you may wonder why this is called with loop fusion. Well, this is called with loop fusion because it is essentially the same as doing loop fusion in the imperative world. And that's why this is called with loop fusion. Okay. Now, when you want to generate code, you have to make choices again. Right, and so all the choices that we have made initially were based on common wisdom on how to make sequential code fast. Because first of all, we needed to demonstrate that you can even get close to sequential performance. Because why bother with parallelism if your sequential performance is factor 10 out, right? So then you have to do lots of things. You have to avoid branching in the innermost loop. You have to maximize locality, and then you have to think about whether you should have flat or non-flat index generators, and this later decision depends again on what kind of index accesses you find on the inside. It's non-trivial, and it took us a bit of a time to really figure this out how to do. And I think we have a reasonable state that we have reached there. So I'll try to speed up a little so that we can make it in time. Now, when we then said we want to do multi-threaded execution, then the first problem that arises is you have to choose the level of parallelism. We all have to do this. I mean, we are blessed because we have the data parallelism there. That means we have parallelism galore, but we have to choose. We have the freedom to choose. And here, it is really nice to have this n-dimensional representation. So we don't have to I think Futag, for example, does something like incremental flattening. We don't have to do any of this because we have the n-dimensional nesting available, and then we say, okay, we just do the outer one or the outer two or the outer three. And also the shape specialization here really pays off, because if we know how big the iteration spaces are, these decisions are easier to get right without having to resort to some empirical testing or optimization in time. Last not least, the multi-thread backend is actually quite, how should I say, lenient in requirements, because most of the optimizations that you do for the sequential backend are good for the multi-thread backend as well, because, in the multi-thread case, you have sequential engines that are running, you have coarse grain, so that's a good thing. So going multi-threaded it is a lot of work, and there's lots of further details that need decision, and there is again papers on this how we have achieved this, but that is doable. Then what happened is we said, okay, we want to we have this here goal that we say we want to have different backends, different architectures, all has to work fine. So the next thing we were looking at, obviously we couldn't miss out on the GPU hype. Okay, so first thing is, okay, we have to identify which goes where. Which array lives on the host and which one lives on the device? And when are these communicated? And how are these communicated? Oh God, there's no notion in our programming language about memory or memory locations. Okay, to automate these decisions, one of the things that we can do is we can piggyback on the type system. That's good, because the type system gives us shapes, gives us information, and so we may be able to do this. And then, you have to figure out how do you optimize transfers. So what happens in loops, can you keep data on the GPU, or when do you really have to transfer things? That is all not exactly trivial, as you can imagine. Likewise, you have to identify kernels. This is kind of the same as figuring out what it is you want to do in parallel. Now, the difference is the choices here are different from the choices that you want to do in the multi-threaded version. Okay, why? Well, kernels they like fine grain. That's great, because they want to have homogeneous computations. They don't want to have conditionals, and they don't even allow for all kinds of operations in there. Okay, again, you can piggyback on the information that you have. So having the n-dimensional information available and having shapes available is a big gain. But it is still a lot of extra work, which is kind of orthogonal to the other work that we've been doing. All these high-level transformations that we did in order to fuse and fold with loops still has to happen. But the problem is you may want to reconsider certain of those decisions, because it might be cheaper to recompute things rather than load things from memory again. Ugh. Horrible. And then, when we started looking into this, it really felt like the empire is striking back. Why? What is happening? Well, what is happening is, for example, when you have grids, interleaved grids on which you want to compute, then in the sequential backend you want to have temporal locality, yeah, and that means you want to interleave your grid computations. Now, if you have a kernel, you don't want to do this, because you want to have two separate kernels that do this. But this is a fundamental change in the way you generate the code. So our intermediate stage of the optimized with loops means we have to break off now and generate different code from the GPUs. And there are hundreds of trade-offs. A few of the trade-offs we've been talking about in the paper 5 or 6 years ago, and we still do not quite know. And we hope that some machine learning supported automated tuning could help, but we have not really looked into this yet. Then we come to memory management. Memory management, again, you have choices that you can make, where you have to decide what you want to do. So we have decided we want to have flat array representations in memory. That has many advantages with respect to memory access patterns. It's also one of the results from the Csr project in the 80s that they said nested representations in memory are not exactly a good idea in terms of high performance. So then the question was, okay, how do we make sure that we can reuse and update in place? And the very natural choice here that is screaming at you is reference counting. When we don't want to do stop the world garbage collection, no, but we want to make sure that we can update whenever we have unique access, We don't want to enforce this on the programmer, so we don't want to require the programmer to make sure that an array is in fact unique. We want to do this under the hood. We infer whether it's unique or not, and then we decide whether we need to make copies, and where we can't statically infer it, we dynamically check. And that is a very good strategy, in particular when having flat array representations. That means you have very little reference count. You know, we don't have any cyclic references. So it is, you know, the nirvana of reference counting, you could say. Oh, that's great, fantastic. So the challenges await you when you have nested with loops and things like that. But, you know, this can be dealt with. And you know, this paper is one good way. Now, if you go multi-core, and I have slipped this slide in the break because it kind of reminded me of, or it gives a potential answer to one of the questions that you posed to Phil. If you have a single-threaded computations, then, you know, this is the flow of computation here, and then you do some reference counting operation on some arrays that you're dealing with. In essence, if you call a function with an array, then you increase the reference count, and whenever you use it inside the function body, you decrease it, and so you have an up-to-date reference counter. That's fine. If you have a data parallel program, then the good news of the data parallel program, in contrast to what the task parallelism that the Haskell guys do, you know, if you have a data parallel program, then what happens is from the sequential case, you go into the parallel case. And in the parallel case, you have multiple threads, and the multiple threads want to do reference count operation. But what kind of reference count operations do they do? Well, first of all, they might allocate arrays. If they allocate arrays, the good news is arrays can't escape the scope of the data parallel operation. This is guaranteed. Woohoo! Functional semantics, I love it. Right? And that means I can have a thread local heap here. That means I can do reference counting here and there at the same time, and it doesn't hurt me. I don't even need to have a lock on it. Oh, hang on. What is with the relatively free variables? Oh, yeah, there is the relatively free variables. But what is a relatively free variable? It's an array that exists out here, and which is referenced inside there, most likely by almost all of the threads. What this means is I can only reuse this global thing in one out of the n cases if I have n-fold parallelism. That price is too high. So what we do is we simply turn reference counting on relatively free variables off while we are in the data parallel section. And if we do so, the good news is we don't need to lock, because we know that reference counting is only happening thread local ever. That's beautiful. That's really beautiful. And we end up with what we call bimodal reference counting, right? So reference count either works as usual, or when any object goes into as an argument is a relatively free thing inside a fork, which means essentially with loop execution, then we turn the reference counting just off. So if anybody wants to do a reference counting operation, it just says, oh, it's in no RC mode. Forget it. I'm not doing it. Simple solution, very nice. So reference counting, fantastic, right? Then we ported the entire thing to the GPU. What can possibly go wrong when going to a GPU? Well, in essence, it turns out reference counting is not the only problem, but it matters how many allocations you do. If you want to have the best possible transfer rates, you need to minimize your memory allocations, because allocating memory on the GPU is costly if you want to have asynchronous transfers, and they are more efficient than the synchronous transfers. I leave you some references here, so if you're interested, you know, just follow it up on this. And then the story goes on. You know, the more architectures you look at, the more fun you detect. If you want to do vectorization, you want to fiddle with data layouts and distributed memory, you have to have other support for things. We have looked at massive multiprocessor systems on chip. And again, the code generation is vastly different. Even the transformations on higher level become painful. If you're interested in the details, please do go to our homepage or just drop me an email and ask, and I can point you to the relevant things. So let me try briefly to get to the conclusion. So what is now about this carrot? I think we do come closer to the carrot because we find solutions, but we really have to be patient. We have to be way more patient than anything that has been done before. You know, if you look at high performance Fortran, you know, 6 years, that's ridiculous. 10 years, it's ridiculous. You know, it needs a lot of time. And anybody who is trying to do this knows that it is way harder than it seems. And if you win a single battle, right, or a single hill, that doesn't mean it works for the next example, right? Because we have to explore these design spaces in detail. And to explore them means you have to bring all the optimizations together to really see what the impact is. And I think there's one thing that I would really like to see happen more, and that is we need to have more cross-project comparisons. We need to figure out, you know, if you make a certain choice in the design, and I try to outline a few of the choices that we have made, what is the real impact? And it's not measuring how fast someone is or isn't it on a certain example. It is about, you know, what are the consequences of these choices? An honest discussion about, you know, what aspect of the design that I'm looking into really sucks because, you know, it creates problems at this front, and does the other approach possibly help me on this front or not? And that is something that I would like to see. I still believe that functional high-performance computing is the key to low-carbon computing. We just have to bring this patience to the table. And I think a good sign to this is if you look at the imperative world, you see that things are getting closer together very slowly, but it is moving. So I'm not yet the desperate rider of this horse. I still believe in the carrot. Thank you.
Thank you very much, Bimodal. We do have time for a few questions, and then I think we can also continue in the lounge. There should be the Fhpnc table. So for the questions again, if you could type the questions in the Q&A tab of the conversations. Maybe in the meantime, we're waiting for more questions. Bimodal, you mentioned basically that like with dependent types, you should be really careful what you ask for because it's nice and fancy and you can do a lot of things. But on the other hand, it's very easy to make it too complicated for the users, like your industrial users. So I was wondering, do you actually have a wish list from these users, what kind of features they want?
They mainly, that's very difficult to say. And, you know, I mean, you never talk to all the users in the world. That's the first problem. It really depends on the field of applications that you're talking to. I would use a slightly different approach. I would look at what people do use. And you see that people use systems that are easy to program. You know, Python is a wonderful language because it gives you the freedom. You can just do something and then see what happens. People use MATLAB, and you have almost no guarantees there. I hope there's no MathWorks employee in here, or if he is, you know, speak up. No, and I think that there is the problem. It needs to be easy to specify, and it needs to be intuitive to be understood. If people have to learn how to introduce PyTypes, I don't think this is possible. At least not, you know, on an intermediate level, this may be fine. This may be great, but not for the end user.
Federico Pizzuti has another question concerning the unpalatability of dependent types to users. Do you believe it is because they require too much information to be provided, or is it due to the way the information is encoded that is the scary types?
Yeah, if I would know the total answer to that, that would be great. I think it's a combination of the two. I think that we could find ways to make it palatable in the way how we specify this. And if you look in the developments in the gradual typing of the record system, I think they do very good stuff in that direction, where you can annotate a little bit, but the type system will not immediately kick you off the board if it can't satisfy everything statically. And I think that should be the route we should go. Which doesn't mean one shouldn't go dependent types at all. I mean, I think it is fantastic if you can prove these things, but I'm not sure how to separate this from the ordinary user. And a good answer would be very much appreciated.
And Thinks and Trolls has another question, basically. So in hindsight, what do you think are the largest mistakes in design implementation approach?
Largest mistake. I think it is we repeatedly make the same mistake, and that is that we always start from the easy case and then try to widen it in hindsight, and that makes it difficult. So to give an example, in the beginning we said everything needs to be AKS. The world was beautiful, it was easy, and then we said, oh no, we really want to have modules. Oh no, we really want to have generic functions on the modules. And then the entire subtyping business came and that was painful. Is it a mistake? I don't know. I would love to know. I would love to learn whether it was, for example, a mistake to have this idea of keeping the n-fold nesting. Because if look at FUTAC or lift or accelerate, I think, if I'm not mistaken, essentially you always look at an n-fold nesting of your one-dimensional maps, right? And so you're dealing with nestings of maps. Whether that is more convenient or not, I don't know. We have examples where we're dealing with grids and coarsening and widening of grids, and I can't really see how that would compare. I would love to do that. I would love to find this out.
Yeah, Accelerate also has this basically shape polymorphism in, but because there are other restrictions in the language, I think the problems are slightly different. But one thing I really liked, you mentioned in the end, and I think we should pick that up later on in the discussion, is that we should really come together and talk about the pros and cons of our design choices. Because as you said, like, it's such an incredibly difficult problem. And I think we could learn a lot by talking more about what kind of design choices we made, what the implications were, and so I would really love to pick that up later in the last session today. Then I would like to thank you again for this excellent talk, and as I said, let's meet back on the Fhpnc, and we have to find a shorter abbreviation. I always struggle with the name of this workshop. So let's meet back in the lounge for more questions.
Yeah, thank you. See you in a bit. How do I get there? Interesting question. Looks like I have to know.
Hello.
So the Q&A thing for me is basically stuck on the two questions on yours and Federico's.
Yeah, that's because they no, okay, that's weird. What are you sorting by and viewing by? right now I'm sorting by latest and viewing unanswered, and it's not showing anything because it just marked.
I had view all, so let me view unanswered. Yeah, because now it's new session, it doesn't show anything. Or if I view unanswered, I see nothing. Maybe because I marked the two questions I could see, yours and Frederico's, I marked as answered. So maybe, I don't know.
Anyway,
yeah.
I will do the rest of the introductions and questions, right?
Yeah, yeah. Yeah. It's nice. It's really good participation. I'm pleasantly surprised. Do we have this speaker?
No, not yet.
Not yet.
Oh yeah,
I think it's Adam, right? Adam who's going to give the talk, or
yes, he just joined.
Ah,
yeah. Hi.
Hi, Adam. Should we go basically on stage and try out screen sharing? I mean, that's one thing which.
Yeah, let's do that. I'll try sharing my tab.
Works for me.
Cool. Great. Maybe.
All right, so let's wait for another minute for the actual starting time. Okay. Can the audience hear me? I got a little bit disconnected from what's going on. Yes, the audience can hear me. Great. Okay, so welcome to another session of Fhpnc, our last one with regular presentations. For our first presentation will be by Adam Paske on parallelism preserving autodiff for second order array languages. This was one I've been looking forward to myself. So here we go, Adam, the stage is yours.
Yeah, thanks a lot. Yeah, sorry, the title is a bit of a mouthful, but yeah, anyway, thanks everyone for coming. So today, yeah, we've basically been exploring sort of some new avenues in array languages, and one of our specialty, both for me and my co-authors, is working with automatic differentiation. That's the autodiff part of it. We're all at Google Research, and thanks for having us here. So just to start with, most of you are probably aware with what I'm going to say in the first few slides, but just to better motivate sort of the landscape of what's out there and what's not out there. If you really just go to I don't know, if you start Googling for array languages, what you find most people use is something like MATLAB, or one of the really whole explosion of Python-based sort of DSLs for array computing, and most of those really look very similar. The basis of them is something like you have a whole bunch of basic math ops. Then you might have, for example, a few hard-coded reductions, like you'll have probably plus, times, max, and minimum. And then you will have some other operations which could be expressed as compositions of those, but are included for efficiency. For now, I also set aside things like indexing and conditionals and loops. Those do require some other care. If you're interested, for example, in differentiating slicing, you might be interested actually in one of the in the paper that we also with the same authors actually as a subset in the main ICFP track, because we talk about it there. But so one really common property of all of those is that there are no user-defined functions as arguments. Like all of those are kind of, because they're usually embedded DSLs, which kind of come with prepackaged code before, and the host languages that you use to call them are usually relatively slow. You probably don't want to actually end up calling user-defined functions. Users instead are expected, if they really expect high performance, they're expected to like compose their program out of like the primitives that are provided. But the good part about it is that actually AD is, well, largely solved. I mean, obviously there are extensions, and actually one of the things that we are working on is improving the stuff that's already there. But kind of the basic stuff that gets you most of the way is already there and has been there pretty much for years now. But obviously, user-defined functions arguments are really nice, and they actually enable you to do a whole bunch of interesting things. And so most of the languages that you actually find at the workshop here, they do have primitives such as map, which applies a function to a collection of things independently. You have reduce, which just combines a whole bunch of elements with a binary reduction. And you have scan, which is like reduce, but except you output the element at every step. And the really nice thing about all of those is that, well, maps pure functions are generally always parallel, and also reductions and scans, if the binary function is associative, you can also evaluate them in parallel, which makes them a really good basis for, for data parallel languages, for compilation to GPUs, right? And so this is really the scenario that we're interested in working with, and this is kind of the language that we've defined in our paper. It's really just roughly lambda calculus. Here at the top, then you have the array combinators with map, reduce, and scan being kind of the main ones. The rest ones are first order, so kind of they're less interesting from AD point of view because we already knew how to do those things. And then there are sort of special combinators for AD purposes, and this is what I'll be talking about a bit later. But so we all know that this is a nice basis. Something like a mapmul is really just a composition of two maps and a reduce. But the benefit is that once you start code generating, you can actually do like other semi-rings, and you just expand a lot. So just because it's so worthwhile, just because everyone here probably has interests and is working in something like those languages, we figured out that actually looking at how AD behaves, and also we're working on similar languages, so figuring out how AD behaves on such languages was just an interesting challenge for us. So before we get into like what works and what doesn't, let's just quickly look at what AD actually is. So generally, we will be working with functions from some A to B, and if the function is differentiable, for now, we will assume that all functions are differentiable and that all of the types, both for inputs and outputs, are vector spaces. So just to recap, actually the properties that I need for this presentation are, there's like a 0 element, which is a neutral element of addition of things. And so if A and B are vector spaces, okay, for simplicity, they have to be vector spaces. In reality, they can be something else. But the derivative then is a function with a very similar signature, except you do append, you do kind of duplicate the input argument. And the semantics of this are, well, if you evaluate f, you have to give it a point and you get some output. And derivative is similar. Derivative still needs to know around which point it is supposed to work. But then once you give it a point, it also needs kind of a delta, like a change in the input space, right? Which is, let's say, a nudge, a small nudge you might apply to the input. And what it will output, the derivative function, is not the actual output of the function. It'll actually output how, like, if you nudge the input by the second argument, what is the expected, kind of what is the approximate change you will see in the output argument, right? And just to kind of put this all together, all of this is summarized with something like a first-order Taylor expansion, where, again, if you have function f and you nudge some x by an epsilon, where x is the first argument and epsilon is the second one, what you get out is the value of that function plus kind of the change that the derivative function estimates.
Or, because, so that was kind of, sort of, hand-wavingly, I explained the semantics of what this is supposed to be. But if we are to reify this actually as a programming language function, it looks something like this. You have forward mode, AD is one of the two modes. We actually do like to call it JVP for Jacobian vector product, because that's kind of what it corresponds to semantically. And so it is actually a function transformation. You can give it a differentiable function as the first argument, and what you get back is another function, which actually takes as input, you take the x and you take the sort of sensitivity, the perturbation on the input, and what you get back, what you get out is the output of the function and the sensitivity of the output to that perturbation. It's just more efficient oftentimes to just evaluate them together, which is why the signature looks like this. So okay, so that's kind of roughly what, that should give you some idea of what AD is supposed to be computing, and that is forward mode AD. We'll also get to the other mode of AD a little bit later. So what are the AD systems that we do have today? So the stuff that we know already is, well, we know how to do automatic differentiation of languages that are, of array languages that are first order, where you have no kind of user control, because then, well, you have just a finite set of primitives that you have to handle, and you might need to extend it a little bit to have primitives to express the derivatives. But usually at some point, all of those languages kind of reach a fixed point where you have a language which is closed under differentiation, and you can compute like arbitrarily high derivatives. And if you have just something like 4 reductions, you just sit down with pen and paper or some symbolic tools, and you can just work out what the derivatives are. Then there are systems that could handle something like second-order languages, but they do not work on as high level as the SOAC programs. So a good example here is something like Enzyme, which works on the level of LVMIR. So it's essentially, it's essentially AD for kind of low-level sequential languages with sequential semantics, and what you get out the derivative, again, is sequential semantics, right? So most of the languages that we talk about here probably will lower to some step to a similar language at some point, but we might want to do AD a bit earlier, simply because it gives us more flexibility to do optimizations than this late. We know that scans, we know that reductions have some nice properties, and we might want to use them. We might want to also apply those nice properties to do optimization on the code that AD produces. So just dropping this far down might already be somewhat unacceptable. Interestingly, there are also other systems which can handle something like second order, so arbitrary, user-provided kind of monoids for reductions, but they do require extra static knowledge about array sizes. It's essentially, the idea is that if you, for example, know the array, the size of the array, and if you know the user specified function, this might already be enough information for you to pick some strategy of actually evaluating those, something like a scan. And so you can just unroll this strategy because exactly how many elements there are, so you can just unroll the program, and then you can differentiate through this kind of like a first order, right? So essentially you can normalize your second order program into a first order program roughly if you have this extra information. But this doesn't always hold. In particular, in the language that we're interested in, DEX, we do not want to assume static knowledge about array sizes. We do not want to unroll those things before AD. And so roughly the goal that we want here is that the AD rules of map and scan should involve just map and scan. Another nice property of having something like this is that, well, if the derivative of map is another map and the derivative of scan is another scan, then your system hopefully will also be closed under differentiation. And again, you not only support first-order derivatives, but also arbitrary order derivatives. Also, I will not be really talking about reductions, simply because, well, you can see a reduction is a scan post-composed with a projection of the final elements. And so, just for simplicity and for the sake of, conserving time, you can just view it as a special case. OK, so how do you roughly implement AD systems? What you do, one nice thing about sort of derivatives is that we have the chain rule. And the chain rule is essentially a theorem that says that if you have two differentiable functions and you compose them, then it's also differentiable. And the derivative of the whole of the composition is some expression that involves the derivatives of the individual elements. And so the nice thing about this is that it is actually sufficient to just specify the sort of rules for how you differentiate language primitives. And then, from those, you can inductively build up the derivative of larger programs through this composition rule. And so really our task here, the second one is nothing new. This is well known, and every AD system does this. So really what we have to do is just specify rules for the language primitives. And in particular, we do know how to do things like differentiating first order array programs. So really the interesting cases here will be map and scan. Case of map, fortunately, is fairly simple. Again, kind of calculus 101 is if you have a bunch of elements and you apply, if you have a vector of a few elements and you apply a function kind of component-wise to this vector, then the derivative also is computed component-wise by taking the derivatives of every individual function. So the rule for map is fairly simple. If you have a map of f over x, then to compute kind of the sensitivities and the outputs, what you do is you map the JVP of f over the arrays x, and kind of the x prime is like the epsilon, the kind of nudge, the perturbation to x's that we're propagating as we're computing the derivatives. So now the question is, what do we do with scans? This is a little bit more involved, mostly because the biggest issue that you really find when you do this is the JVP of f. If f is associative, right, because we assume that about the binary functions that we give to scan, then JVP of f is not just straightforwardly associative, really. If you take the associative law, right, so for all x, y, and z, this equation holds. The for all is important because this means that in particular, it is valid to just differentiate both sides of this equation. You get something like this. And so this looks very similar. This is a kind of like an associative law on those perturbation variables. So if x is the some point we're interested in, x prime is the perturbation we're applying to x, then this looks very similar to an associative law on the perturbations. The only caveat here is that we have those. Oh yeah, sorry. Actually, one thing that I should have mentioned is, so those derivative functions, they have two inputs, but I kind of treat the second input, the perturbation, as like a more important one when talking about derivatives. And also, I will indicate this in a notation where the first argument is applied in the subscript, and the second argument is applied kind of using the mathematical function application notation. This is also kind of this is also because you can view the derivative as like a family of functions that is indexed by the points in the input domain. And so this really selects one. This x really selects one of the derivative functions, in this case around x, and we can then keep evaluating that function around with different perturbations. So, the notation here essentially says that if you take a derivative of circle dot, you can instantiate it at some points for its both arguments, and then you can apply it to some two sensitivities to get the sensitivity of the output. And so, getting back to this pseudo associativity law, you can see that it's really not full associativity because the four functions we have here are four completely different functions, because the indices, the sort of members of the family of the derivatives of circle dot, we just select four completely different ones because the primal points that we have in subscripts are completely different. And so, it's not immediately clear how to do this, but really it's not super complicated either. You can just do kind of the classic trick of, once you have just bundle some extra information, and in particular, if you just pair the values with their sensitivities, like if you take pairs of x and x dot, you can write out like a circle plus operator, which just applies circle dot on the first one and then applies the derivative on the appropriate points, propagating it through the second component, and you can actually prove that this is associative. It's not super difficult. You just use this pseudo-associativity rule, and it all ends up working out. This is kind of the expression you can use to differentiate a scan. It doesn't end up being too bad. So, okay, so I guess this is roughly what it takes to do forward mode differentiation. I guess at this point you might be wondering, why is this even a paper? But this is not where the problems end. So now that we have AD, one thing that we would really like to do is run gradient-based optimization. That's kind of the workhorse of AD. That's like really what powers most of machine learning. Roughly, the idea is that if you have a function from some A, which might be, I don't know, an array of billion floats that are parameters of some optimization problem, and that outputs a single scalar, which kind of indicates how well you're doing, you would like to extract gradients of that function. So given any input, you would like to kind of figure out what is the direction of the steepest descent, for example, in the function, and then kind of use this as a heuristic to move in the parameter space in the direction locally in the direction of the steepest descent, hopefully reaching some local minimum. But the problem is that if you look at JVP, in this, if our function is from some a to a scalar, if we substitute the scalar for a b, kind of a simple like type-driven proof, not even resorting to mathematics, basically indicates that if you evaluate JVP, you can only get like at most 1 or 2 scalars out of it, right? And the gradient in particular, if you have 1 billion parameters, should have 1 billion elements, right? So you will have to it is possible to reconstruct the gradient using JVP, but it will have to evaluate it repeatedly, and in particular, many, many times, which is obviously not desirable if you have, a large neural network or something. So there's an alternative formulation to JVP, which is linearize. So given a function, you can actually get back it kind of unzips the both parts. So if you apply linearize to a function, you get back another function, which takes the same input and gives you the same output, plus the derivative function, which is not evaluated immediately. You kind of get it back. And what's important is I use this funny arrow to actually indicate that it's a linear function. It's not just any arbitrary function. All derivatives are linear functions, which is actually really important because linear functions have transposes. And transposes are really nice because they let you swap out the sort of domain and codomain. And so in particular, we would like to have something called VJP. So JVP is Jacobian vector product. VJP is actually vector Jacobian product, which is just like linearize, except we kind of swap this one, swap the order of the arguments to this function. So if we could transpose it, in particular, it is possible to do it. If you implement VJP, you can just compute the gradients using a straightforward expression, and then you're done, right? So given that forward mode wasn't that difficult, it shouldn't be too hard, right? And it turns out that it's actually a nightmare. Like those are the rules for scan and reduce, and I don't know. It was difficult to work them out. I actually implemented them once to just make sure that I didn't actually end up having some typos in here, but it's definitely not satisfying. So this is way too complicated. Like this does not feel like the right solution for this, even though it is a solution. It does not feel like it's really a right solution just yet. And also, what's even kind of, I don't know, what's silly is that it doesn't even have the right asymptotics. There's like a nice theorem in AD community which says, I don't know, we often like to call it cheap gradient principle, which basically says that in your programming language, if you take all programs for any there is a constant that is independent of the program that you pick, such that the cost of evaluating the something like a JVP of f or VJP of f is at most that constant of the cost of evaluating f, right? And the issue is that this system doesn't even satisfy this. There is somewhat a nice bound you could derive, which is something like the sort of nesting scans in the binary reductions of other scans blows up this constant, and as deep as you nest, you can blow up this constant as much as you can. So it's not like I would assume that those are relatively exotic programs, so it's not that big of a deal, but it's still somewhat unsatisfying that we can't satisfy this, because other AD systems generally do satisfy the rule. So, I'm diverging from the paper at this point, but I just want to give you just to finalize, I just want to give you an outlook on what we think about what we should do as next steps, but this you will not necessarily find in the paper. So both JAX and DEX, which are the systems that we're working on, decompose reverse mode AD into 2 steps, into linearize that you actually saw before, which is kind of forward mode. And then there's another transform, which is transpose. So it's not like VJP as an atomic unit. VJP is actually implemented in terms of those as a composition of 2 other sort of program rewrites, which actually separates the concerns and makes them much easier to think about. The question is, can we apply this to SOAC languages? And for reductions, I think I worked out a relatively OK thing, but it turns out that for scans, it just doesn't seem to apply that nicely. Basically, scans just seem like a really weird primitive from the AD point of view, where the sort of AD system ends up fighting with the compiler, which is way too much control over there are so many different ways to reassociate the expression that AD would like to have some visibility into this, but at the same time we don't want to constrain the compiler too much, because that is the beauty of scan being so high level, right? So what if scan is really just the wrong level of abstraction for something like differentiation? Just to give you a sort of very rough estimate of what is the issue, what AD does is when you have some operator, like the green box here is some operator with 1 input and 2 outputs, but you can see that it could lower it to some other operators inside. Really what you're doing when you're differentiating is when you do reverse mode, you kind of construct a very similar program, except the data flow is reversed. This is why it's called reverse mode. But the problem is that there are actually additional data dependencies that cross from those inner operations of the primal thing into the sort of data flow graph, let's call it, of the reverse mode derived program. And if we're talking about scans, we don't get to like necessarily make up arbitrary outputs, right? Those might be some intermediates that are hidden in the implementation of the scan. We don't get to like output them. But we really would like to have those arrows for the sake of efficiency. But because we can't have them, the best thing we can do is we end up just recomputing some things that we compute for the function while we compute the derivative. And that is roughly, I think, what ends up causing the blow up in complexity of the programs. And that the reason that we can't have those arrows is what prevents us from nicely decomposing the sort of reverse mode differentiation into linearization and transposition. So really the kind of research question, I guess, that follows from this paper is like, what is the highest level language that still has the nice properties of abstraction of the SOAC languages, but still like admits nice and cheap AD? So in summary, like in the paper, we do outline how to do forward mode and reverse mode, or JVP and VJP of SOAC programs. But the VJP is both really complicated and not even as efficient as you could probably make it up. So we do actually, I think, have a language that satisfies this. We just didn't actually have time to like write it up properly. But if you're interested, like we're happy to talk about it. But so yeah, essentially the follow-up is to just try to come up with some different way to formulate a scan, like a different signature for it, or maybe as a composition of some other primitives, and then try to decompose the like monolith of VJP, which just ends up being really complicated, into linearization plus transposition, which hopefully should make it both easier to think about the problem and fix the inefficiency issues. All right, so I think we still have 5 minutes for questions, so seems like a good place to stop. Thank you.
We have some questions. I'll put the first question on stage. Would defunctionalizing scan help?
Right. I think it would. That is roughly what I was hinting at when I was, I mean, assuming defunctionalization, like how would you defunctionalize a scan? Defunctionalizing a scan probably means that it just expand its implementation and like inline the function or something like that. And that is roughly this point, right? Where, yeah, it would, but you do have to commit to an implementation before AD runs. And it's not always possible to commit to a single best implementation right ahead of time. So yeah, and this is how, for example, JAX implements user-defined associative scans and reductions. But you know, I still wouldn't consider it like a full. I wouldn't consider it AD for SOAC programs because you still have to lower the SOAC program into a first-order program.
So I can actually, I will follow up with a small question. So scan doesn't, if you just worry about the asymptotics, then you don't need scan as a primitive. You can write it as a sequential loop, a map, and a scatter. You need some kind of scatter then.
Right.
Are those more susceptible to reverse mode AD then?
Yeah, good question. Well, map certainly works perfectly well, and scatter also shouldn't be too bad. I mean, the question is, you know, what happens on something like write conflicts? But yeah.
Yeah, but in this case, you would actually know it's a nice, well-behaved scatter. Okay. No conflicts, no overrides. It's kind of
if you decompose it that way, then yeah, that could work. I mean, if you have a good and efficient implementation of scatter that would be competitive with, you know, something like the scan algorithms, then I think that should work. I haven't thought about implementing scans that way, but if that's like a good idea, then sure, that could be one way of working around this.
Well, the keyword here was asymptotically optimization.
Right. Yeah. Exactly. So yeah, that's what I'm thinking about. So, you know, we're really interested in like differentiating the fast stuff and not just the asymptotically fast stuff.
Well, the next question is actually mine. So, is there a similar proof that you talk about the proof that reverse mode only adds a constant overhead? But is there a similar proof that reverse mode even preserves the parallel asymptotics in principle?
That's actually a great question. I haven't thought about this, and I haven't seen a proof. One thing that, so basically AD is funny because pretty much everything about AD has been worked out like in the 80s, but not AD on parallel languages, which is like the niche that I think has still a lot of gaps. And so I will not guarantee you that this proof doesn't exist, but I haven't seen it, and it might be a fun thing to derive. But I expect that if you work out, I mean, if you can express the derivative of something like a map as a map and scan as a scan, then I guess it should preserve the parallel asymptotics as well. It might just be a constructive proof of something like that, right?
Yeah, I think the big question is that when you're gathering together all of the that's an accumulation, so that's a reduction in general, and that has logarithmic span.
Sorry, when
you are reversing the data dependencies, what was once many uses of one value, which we say is constant span, becomes an accumulation of many values into one, a reduction, if you call it a summation, which has a logarithmic span. So my hunch would be that from the parallel asymptotics will be a logarithmic factor worse.
I mean, yeah, there you go. So I guess the answer is no. I mean, you can just differentiate a program which broadcasts a scalar, right? And there you go. Like, it doesn't preserve it.
Right. But then the question is that logarithmic dependency?
Yeah.
And you might argue also that broadcasting being constant span is maybe also not really reasonable for a large enough machine.
Right.
Okay. Okay, so there are no more questions from the audience, so I will ask one more. This language that you mentioned that you're working on that handles this better than in the paper, is that language just DEX?
Sorry, which language that handles? Right. Yeah, this was heavily inspired by DEX because we've added. So previously, DEX only separated reductions with like 0 and plus as being the monoid, because that's what we really want for AD. I mean, we've added this for the sake of AD, but we ended up just using it in a bunch of places in just user space. Like we wanted to write programs with this and with arbitrary reductions. But then the problem was I had to write an AD rule for this, and I had to figure out like how to differentiate arbitrary reductions, and it didn't seem like people have been doing that. So this was really the thread. But yeah, it was very DEX motivated, and even though DEX is not combinator oriented, I just figured that since the DEX paper only has been published like in ICFP on this track, it just seemed better to frame the problem as differentiated of SOAC languages, and they're so close that it's really almost the same problem, I think.
Yeah. Well, thanks again for a nice presentation. I'll give you a little bit of applause again, and then
thank you.
Kick you off stage and make room for the next speaker.
Cool. Thank you.
It seems that my camera is not working.
It's not working from my point of view, at least.
I can try reloading the page, and then we'll see. Okay, it doesn't seem to work. Oh well, then I will just share my screen like that.
Right. Yes.
Yeah,
okay.
try.
So this next presentation is also on automatic differentiation by Tom, in the context of the Accelerate EDSL for Haskell.
Yes. So given that this topic is fairly similar, or at least in a similar direction as the previous talk, I will be skipping over a few bullet points in my slide, but it should be all right. So what we're talking about is reverse automatic differentiation for Accelerate, which is a different language than DEX, obviously. And this slide is just a bit of a summary of why you would want automatic differentiation in general, which was also hinted by Adam a bit, which is basically that there's a number of domains that allow you to specify things, specify certain subroutines using programs, for example, machine learning, but also Bayesian statistics. And you might want to, if you want to do some kind of optimization or inference on those things, you might want to differentiate those. And in practice, the kind of differentiation that you need is that you need gradients of functions, and the
the variant of automatic differentiation that you then need is reverse mode automatic differentiation. Hence, that is the variant that I will be looking at. And we're doing this on a functional array language for the reasons that should be obvious to the people in this workshop. And the functional array language in general, in this case, is Accelerate. And let me briefly, for the people who aren't too familiar with Accelerate, tell a little bit about how that works. So this slide will describe the core language of Accelerate, which is slightly different from like the surface language of Accelerate that users program in. But yeah, it's the language that a compiler transformation will work on. So it is a purely functional second order array programming language. And this second orderness is as Bimodal has alluded to earlier, is a choice that Accelerate makes. And that is that you don't have syntactic nested parallelism, but instead you need to use rank polymorphism. So we have like the standard array of parallel constructs. You have the standard like functional programming situations. This is a small example program, but crucially, like for example, in this function here, this takes 2 scalar arguments, and you couldn't do any parallel operations within here. The compiler will reject that. Because what instead you should do is you should have an n-dimensional array and do this implicit mapping that's going on, right? These scalar functions are in Accelerate called expression functions, and they like at some point in the compiler they actually live in a different programming language, so to speak. They live in the so-called expression language, which has basically first-order arithmetic expressions and the expected things. And crucially, one thing that it has, and what you kind of need for certain applications, is that it has array indexing. And that means that you can, while you can't have parallel operations within an expression, you can, of course, index a free array variable at a particular point, because that is, well, it's not a parallel operation, is it? And this, I want to, in this talk, I'm going to focus on how to differentiate that particular operation, because that comes back to bite you when you try to differentiate programs. So again, we're computing gradients, which is a collection of partial derivatives of the function result with respect to all its input values. So for example, just to give an example of this that should be easy to understand, this is a program that takes an array and computes the sum of squares of that array, which is illustrated here in some mathematical notation. So what's the derivative of it, or what's the gradient of this? It is the partial derivative of the function result, namely the sum of squares of the input, with respect to every single input argument. And the derivative of the sum of squares with respect to one variable in that sum of squares doesn't have anything to do with all the other elements of the input. It's just 2 times that element. Why? Because the derivative of x squared is 2x. So you can write down this gradient program like this. And this could, for example, like be the result of this linearize plus transpose procedure that Adam has described, but that is just like one implementation of doing reverse AD. You can make the program slightly more complicated by adding this array indexing in here, and suddenly you have this kind of scatter going on. And how exactly you end up here is something that I will be explaining. So let me briefly, like what Adam has been discussing in the previous talk is to some limited depth how you do forward mode automatic differentiation and the fact that there is reverse mode automatic differentiation. And I'm going to explain a little bit more about how reverse mode actually like works as a program transformation. There are, of course, like different ways to implement reverse AD that are not as a program transformation, but I'm going to focus on this particular variant. So suppose, for example, ditch arrays for a moment, and suppose that you're working on a simple scalar language where you have a function that takes 2 inputs and computes this formula. So you can write this as a data flow graph, and we're going to do the exact thing that Adam has explained. We're going to reverse the data flow. But we need some values from the original computation. So the first thing that we're going to do in the result of this program transformation is we're going to compute what is called the primal values. We're going to just compute the function as usual, but store all the intermediate values somewhere. And then in the second pass, we're going to have this dual pass, which goes in the other direction. What we're going to do is, remember at the end, we want the gradient of this program. So what we're going to do is for every node in the data flow graph of this function, we're going to compute the partial derivative of the function result with respect to that node. And then at the end, what we will end up computing is the partial derivative of the function result with respect to all the inputs, because those are also nodes in the control flow graph. And that is exactly the definition of the gradient. So the first thing, the partial derivative of this node with respect to itself is, of course, just 1, because that's basic derivative logic. Next, it gets slightly more interesting, because the partial derivatives of addition, like things like this, are just 1. So that means that if you want to compute the partial derivative of the argument to an addition operator, then you can use the chain rule, which I write down like this, to say that the partial derivative of some later result, namely the end result of the function, with respect to some variable x, is the partial derivative of the end result with respect to this addition times the partial derivative of this addition with respect to x. And because this thing is 1, we know that it is just equal to the partial derivative of the addition. So we can copy d6 over to d5 and d4. Multiplication is slightly more interesting, because the partial derivative of a multiplication with respect to one variable is actually the other variable. This thing is this thing. So what ends up happening is that, for example, if you know the partial derivative of node 4, stored in d4, and you want to compute that value for node 3, then you're going to take the partial derivative of node 4 and multiply it by the original value of node 2, which is exactly what I'm writing here. Similar for node 2. And the final interesting thing is that for node 1, we have 2 outgoing connections where I see these double arrows, 1 arrow here. And both are going to add contributions to the partial derivative of node 1. And both are just going to be added together. This is a general concept in automatic differentiation, in reverse automatic differentiation, that you get this addition over here. So, and this is a program, and this program, of course, computes, among other things, d1 and d2, which is exactly like the gradient. So you can generalize this to function to a language that has some array operations, and you can do the exact same kind of thing, where you can differentiate sum to a replication of the partial derivative. For exactly the same reason that you can copy d6 here over to d5 and d4. And you can differentiate through this map operation by combining the incoming partial derivatives, the incoming adjoints, as they're also called, with the original inputs, and then you write down the gradient of this expression function over here. So this is all well and good, and on the next slide, I'm going to get into some difficulty. So this slide you've already seen. This is the Accelerate core language summarized. The green parts, so this works better. So basically, this part, this is important in our implementation. We have an implementation of the algorithm that I'm explaining here. We have some kind of partial, easy cases support for a fold, an associative reduction, and the easy cases of a scatter. But there are some other cases that are definitely not supported. We don't have a derivative of scans, for which I am very much looking forward to Adam and team's approach of doing that. And there are some other basic array operations that we don't support, but those are slightly less common. We also don't support sequential loops, which I will get to later. But we do support array indexing. And how? I'm going to show you. So this program you already saw. So let's add some array indexing, right? So this is a more complicated program, which contains some array indexing. This syntax means take the array B and index it at the index, in this case, 2 times I. So if you differentiate this, like in exactly the same way as we did here, you might end up with something like this, where you compute the primal values, like let's just explicitly add some node IDs. So we can compute the 4 intermediate values of the primal computation, and then we can compute the adjoint values, the partial derivatives of those. But the crucial thing is that computing the partial derivative of this map is kind of difficult, because how is it contributing to the result? It is contributing to the result only through the usage of this variable b, which is here. You don't have a nice combinator that you can just differentiate as a whole, like write down the derivative, fill in the components, and there you go. You can't apply this kind of generalized version of the MATLAB way of differentiation, if you will. You have to do something more interesting, and that's basically this slide. So remember, we had this array B, and we did this generate, and this generate produces a new array. So what does it produce? It's a generate or build in some languages. It builds an array of size 3, where at each index I, the element that is there is the array B indexed at the index 2 times I. So assuming that B is long enough, assuming that the program makes sense, this is what happens, right? This is what it ends up computing. And that's all well and good. In the dual pass of the transformed program, what we have is the partial derivative, the adjoint of this generate call of this size 3 array. And what we want is the adjoint of this array B, which supposedly contains like the adjoints of the values, right? That's what we should compute, but we have this one. But we know what's in here. We know that in the primal there was B0, B2, B4. So we know that here, assuming like that the rest of our differentiation machinery is doing its job, it should have the derivative of elements 0, 2, and 4 of this array B. So how are we going to construct this DP? Well, just by putting the values where they belong. And the rest apparently don't contribute at all to the result, so the adjoint can just have 0 there. And this is why it is a scatter, because this original function was really a gather operation. And when you dualize that, when you reverse the control flow, you also kind of reverse the data flow, and a gather becomes a scatter. And a permute is how accelerate notates a scatter operation, where if you have a write conflict, so if multiple values go to the same destination cell, we want to add those. Why do we do that? Because here, if you in the primal had some outgoing arrows, if B0 was also used in this next cell, then in this next cell you would also have an arrow here back to this cell, and you would have 2 elements ending up here, and you want to add them because it is a sharing of values, and sharing becomes addition in the dual in reverse AD. So on write conflicts we start with an array of zeros, and we scatter onto the array of zeros. The values that we scatter are the incoming adjoints from the generate, which is precisely this array. And we scatter the value at index I to the index 2 times I, where this expression 2 times I is precisely this expression. So you can kind of see how this at least somewhat generalizes, and this is fine, right? So in this derivative of the program, we can fill in the permute, and it works fine, and it gets us a derivative. So this kind of shows how array indexing becomes a permute or becomes a scatter, and it gets more interesting if your program becomes more complex. If this expression function this expression function contains an array indexing operation at the top level without anything containing it. If you have something more complicated like this that contains it inside some larger expression and inside some conditional, maybe even, it becomes more complicated, and you might have to do some more bookmarking, like was the indexing operation executed? If not, we might not even be allowed to do this scattering operation of this particular cell because it might be out of bounds or something. So there's some bookkeeping to be done, but this can be generalized. And that at least concludes my story about this about array indexing for now. So I just wanted to share that we've done some preliminary benchmarking of the implementation. It's implemented as a broken transformation in the fork of the accelerate compiler, and we benchmark using the GMM and the BA tasks of the AD bench suite, which is a benchmark suite of a few programs that are taken from like real world situations. That it might be useful to do AD on, and there are a couple implementations of those particular benchmark tasks in existing AD frameworks, so that it is easy to compare a new implementation with those existing implementations. Because quite a number of those existing implementations only work on the CPU, and because of some technical issues, the benchmarking is run on the CPU. I just want to stress that there's no GPU involved here. And the two benchmark tasks that we implemented, one is a Gaussian mixture model fitting process, which is it's really a test of the reverse AD algorithm, because there's lots of stuff going on. It's a fairly complex data flow graph. And the other task is a bundle adjustment, which has the peculiarity that the Jacobian of this operation, so the matrix of partial derivatives, is very sparse. What this means in practice is that really instead of differentiating the entire program as a whole, the entire data parallel program as a whole, you want to do an element-wise operation, and within that element-wise operation, you do differentiation of a scalar operation. And they have wildly different performance characteristics. So I'll show you the results in a graph. I will briefly describe what I'm showing you here. So this is a log-log plot, where on the horizontal axis you have the number of independent variables in the input, so basically the size of the input, and because of the characteristics of the program, you expect stuff to be kind of linear in here. Because the vertical axis is the running time in seconds to compute like the gradient. So this graph is how we do, and without further knowledge about the task that tells you basically nothing, I'm going to add a few other implementations. This is how PyTorch does. This is how two kinds of TensorFlow do. This is TensorFlow Eager, and this is TensorFlow Graph. These are two versions of a manual implementation in C++ that do not use any parallelism at all, but also do not use any automatic differentiation. It's a manual derivative. So it's kind of a reference implementation in the framework. There is also an actual AD framework for C that can do some kind of broken transformation, and with some manual scaffolding that can produce an implementation that is quite fast. That's this one. There is an implementation in F#, which is a bit slower, but also decent on this graph. And there's a final one that I just want to show for fun. This is a finite differencing implementation, which is completely different to reverse AD in that it actually increases computational complexity from linear to quadratic in this case. And you can see that because the line is significantly steeper, about twice as steep, in fact, in this log-log plot, which means that it is indeed quadratic. So what you see is that this one gets cut off here because it runs into a time limit of the benchmarking framework. But more importantly, our implementation cuts off here not due to any kind of time limit, but because we have a very significant memory usage, and basically we run out of memory. So this is an existing problem in our implementation, and we're still working out how to fix that future work. The next graph is about this BA task, which has very much parallelism in its differentiation of scalar level functions. So we are over here, which is kind of decent, except this is our single-threaded performance. If you actually let us multi-thread, then we end up over here, which is, well, good enough given the other implementations in the suite. So brief summary, this is a very pragmatic reverse AD algorithm, and I say that in comparison to other like combinator or categorical kind of ways of doing automatic differentiation on languages. And the thing that I want to emphasize is how to do this indexing kind of thing, and to show that like this kind of innocuous scalar level construct, when you kind of do that in reverse, it suddenly gets blown up to a full data parallel scatter operation. But there are, of course, some open questions, some that I alluded to earlier. We have a memory usage problem. We don't have a derivative written out for sequential loops. There is, of course, parallelism, but we don't have like actual sequential loops because this has some memory allocation issues for GPUs. Because we do want to at least support a GPU target for accelerate. General derivatives of more primitives and some checkpointing thoughts that I can expand on if someone is interested. So that's the end of my slides, and I invite any questions. I do have some suggestions if you don't have questions. Thank you.
Okay, well, we have 2 questions, and feel free to ask more. So the first question is, what is a first-order arithmetic expression?
A first-order arithmetic expression is an expression that contains the standard arithmetic operators like plus, minus, times, divide, and also any kinds of standard transcendental floating point operations that you might want to support. But crucially, there is no parallelism involved. So while you may use n-ary tuples if you want, that n in the n-ary tuple should be a compile time constant. So only like actual scalar operations.
All right. The second question is mine, and I didn't phrase it very well, but this way of handling array indexing in your reverse mode transformation, does that preserve the asymptotic cost of the original program?
I guess you can ask that question both in terms of like actual work and in terms of parallel span. In terms of work, well, both actually. So like the standard kind of scatter. I believe like the corresponding function in Futhark to permute will be reduced by index, if I'm not mistaken, which usually, if in the good cases, is doesn't have any work beside doing a constant time operation per element that it is scattering. That runs into problems if you have lots of conflicts or something. But that is, yeah, basically the same kind of provisions that you have there apply here too.
But what about creating the target array? I mean, is it sparse? Does permute create a sparse array in the places where you don't write?
Permute, that is a good question. Permute does not create a sparse array in Accelerate, at least not currently. So that means that to actually, yeah. So you might have some array allocations that get introduced, and if you get unlucky with Fusion, then some of those allocations may definitely persist. But I believe that can still be a constant factor slowdown.
Okay, thanks. So the next question is from John Hughes, who's asking, your array indexing was with indexes that did not depend on the data in the array. Would it be a problem if they did?
Very good question. What you're basically saying is that my example is bad because due to the fact that the indices do not depend on the data in the array, you can actually do something slightly more simple than this. Actually, we support full dependency of the array index on the data in your program, and this works unchanged.
Okay. What's the reason for not supporting sequential loops? Is there some limitation of Accelerate that makes it difficult, or is it just not implemented yet?
Accelerate actually has like two ways of having sequential loops because it is split in this array language and this scalar expression language. It has a separate looping construct both in the array language and in the expression language. If you have an array level loop, which is an unbounded loop, it's a while loop. What you could do as an implementation, which we have not implemented, but which you could do, is so the problem is the unboundedness of the loop. If you know the number of iterations that your loop is going to take, then you can allocate an array of destination values in the primal case where you can store your temporary values, and you can kind of scatter them in there, hoping that in-place updates do the right thing. If you have an unbounded loop, then you have to kind of pre-allocate an array, and if it gets filled, you have to resize it or something, which you can do, but it's annoying, and we definitely have not done that. What gets more annoying is if you have a loop in the inside a scalar expression function, because then you basically have lots of loops in parallel, which might not even have the same amount of iterations. If they happen to do so, they can kind of try to split it out so that you can do the same array parallel operation where you scatter the values into a destination array. But if you don't know that, if the number of iterations vary, then you have some kind of non-regular parallelism thing going on, which I don't know how to handle.
All right. So last question, I think it's similar to what you answered before. What kind of indexing do you allow for indirect accessing as well? Can you always statically decide?
Yeah, so yeah, we allow any kind of indirect indexing. You can use any kind of values that you want in deciding what index to index on, even the result of other indexing if you want. What is, I guess, an interesting question is reflecting on how you can speed up the implementation or make the transformation better if the indexing is actually not as dynamic as the general case. And there might be something that you can do there, but that's not something that we've looked into yet.
All right, thanks. We are out of time and out of questions, so that's great. Let's give another applause while I kick Tom off the stage and invite the next speaker.
Thank you.
That was nice. So this is the end of the presentation program at Fhpnc. There is a button on my screen that says that someone has been recording this session. I assume Airmeet. So at some point, maybe recordings of the various presentations might be made available somewhere. Maybe they'll ask the presenters for permission. I don't really know. I didn't even know it was going to be recorded. But the next thing is we're going to do is the future of Fhpnc discussion, which will take place in the lounge at the Fhpnc table. So I'll be closing this session, and you won't be able to rejoin. But please come to the table in the lounge and let us discuss what's going to happen next for Fhpnc together. Okay, and thank you all for coming. I had a lovely time.
Yeah, thank you all for coming. Hope for those who have to leave earlier. Thanks again the PC and the invited speaker, and yeah, see you at the Fhpnc table. So
now we can press this end session button that we were constantly told never to press, right?
Yeah, I hope that this does not kill our table, but that should be okay now.
Okay. I'll see you.